Okay, nice. Okay, so I can start. So thank you so much, everybody, for being here for our second days of activities of the Bingo collaboration meeting. So today we are going to have a series of uh, lectures and talks related with uh, scientific subjects on Bingo. And to start, we are going to have our first talk from from Dr. Zikia Zhang, talking about the bingo structure design of the radio telescope. So please, Dr. Zikia, thank you so much for your time, and it's a pleasure to have you here.
Okay. All right. Let's start. Mm, And hello everyone. My name is Ziqian Zhang, and my topic is structure design of bingo ratio telescope. And today I will introduce the project in in 5 sections. So the first section is background. And bingo telescope consists of a primary reflector, secondary reflector, and the fixed source. And the role of CTC54 in this project. The first one is design and the manufacture of primary and secondary mirrors. And the second one is detailed design and manufacture of metallic support structure of primary reflector, secondary reflector, and feed source. And the last one is the research of feed source. So the Brazilian side has provide the metallic support structure of primary reflector and the secondary reflector, as well as the horn support structure. We will refine the design and simulate calculations based on the model. So you guys can see the right side the pictures, and these are the uh, metallic structure. In the design of Mirror's bingo telescope was inspired by fast astronomic telescope. The idea is fit a surface with planes. That means primary mirror and the secondary mirror consist of many small flat panels. The second section is the design of mirrors. So the mirror is divided into several panel units according to the primary metallic structure connection points. You guys can see the right pictures. That is the size of each panel units. And then the panel units is divided into 6 panel subunits. So the size is on of each subunit is on the right. You can see like each subunit may the size it may be like 225 20 250 2050 500 millimeters multiplied by like 1600 millimeters. In the graph on the left is the divided of primary mirror, and the graph on the right is the divided of secondary mirror. And the panel subunit consists of punched aluminum plates, purlins, and connecting plates and rivets. So for this part, I want to introduce the connection method between panel and the metallic structure. Our first idea is method 1, but after simulation, we find that the weight of mirror is large, so the load on the metallic structure and the foundation is large too. And then we want to reduce the mirror's weight. So after our discussion, we have new idea, and that is method 2. So first, I will introduce the method 1. So the method 1 is the panel units consists of panel subunit and the backup structure. And then panel units connected to the metallic structure. So we can see the right side. This is a backup structure, and you can see that this is a panel subunit. And then we just put the sub panel units on the metallic structure. And 6 panel subunits and the backup structure are connected by trays, bolts, and nuts. For the method 2, you guys can see the right side. So I want first we need to increase the number of steel paths to get more connection points. You guys can see from here to there, and then while the connectors are the connection points of metallic structure. And finally connect the panel subunits to the connector. And there are 3 advantages of method 2. And the first one is the weight of the mirror is greatly reduced, and the load on the foundation is greatly reduced, so the cost of foundation will be reduced. And the second one is remove backup structure will reduce the amount of steel used. So the design and the processing cycles are greatly reduced. The last one advantage is the remove backup structure will reduce the cost of transportation. The third section is a mechanical analysis. We simulate the force on the foundation, and we build finite element model. And the weight of the weight of mirror is 25 kilogram force per meter square, and the wind speed is 30 meter per second, and the snow load is 25 kilogram force per meter square. We have calculated the force simulation situation of each foundation connection point. we compare foundation force simulation of two methods. This page is the result of a primary reflector metallic structure. And the conclusion is the force on the foundation of method 2 is smaller than the method 1. And this page is the result of a secondary reflector metallic structure. And the conclusion is the force on the foundation of method 2 is smaller than method 1. Section 4 is electrical analysis. First, I want to introduce the calculation method of RMS. So the surface accuracy refers to the normal error between the measuring point and the corresponding spherical point on the surface. Oh, sorry. Let's review the divided of mirrors. And the left side is the primary mirror and the right side is secondary mirror. In order to verify that our method of calculation of RMS is correct, we verify that four vertices are on the surface and the RMS should be 0. So you guys can see the result that is in the table. And according to the results, the calculation method of RMS is correct. And we divide flight panel into grids, and the size of grid is 250 multiplied 250 millimeters. And there are 10,000 points taken from the primary surface, and around 8,000 points are taken from the secondary surface. And then we calculate the RMS. So we can see the result that is in the table. And then the table shows the RMS of primary reflector is 1.46 millimeters, and the RMS of secondary reflector is 2.8 millimeters. And this page is compare the electrical properties of elliptical edge and the sawtooth edge models. So we import the models into the FICO software, and the reflector is illuminated by with the Gaussian feed. So you can see the result that is in the table. This is the result of elliptical edge, and this one is the result of sawtooth edge. So the conclusion is sawtooth edge model has no effect on the electrical performance. We used two kinds of software to do the electrical simulation of the telescope. The first one is FICO software, and another one is GRASP software. So I will introduce the FICO software first. We also import the model into the FICO software, and a reflector is illuminated with a Gaussian feed. So we can see the gain, aperture efficiency, and the first sublobe level. The result is in the table. So the conclusion is the electrical performance of flat panel model and the theoretical model is consistent. In for the GRASP software, we also import the model into the GRASP software, and the reflector is illuminated with the Gaussian feed, and we import the vertex into the GRASP software and build a flat panel model. We also get the result in the table. So the conclusion is the electrical performance of flat panel model and the theoretical model is consistent. We compared the results of two software. One is GRASP and the second one is FECO. So we can see the difference is small. So the conclusion is the difference between the FICO and the GRASP simulation result is small. The last section is design of horn. Let's see the requirements first. So the frequency of the horn is 0.98 to 1.26 GHz, and the horn should have simple structure for manufacture, and should be also has fast production cycle, and absolutely should have excellent performance. We compare two kinds of horn. The one is corrugated horn, and the another one is smooth. It's called smooth wall profiled horn, and the result of two horns are on the right side. You see, this is the result of voltage standing wave ratio. The red line is corrugated horn, and the green line is the smooth horn. This is the result of radiation pattern of corrugated. The top one is the result of corrugated horn, and the bottom one is the radiation pattern of smooth wall profiled horn. We can see the result of gain and aperture efficiency of two kinds of horns are in the left table. And please have a look. So we get the conclusion is that the smooth wall profiled horn is better. For the smooth wall, for the smooth wall profiled horn, the horn is made of carbon fiber composite material with foam sandwich structure. Because of the gravity, horn was recalculated based on stress analysis result. The result of gain and aperture efficiency in the red table. Please have a look. And the conclusion is the gravity has no effect on electrical properties. And the smooth wall profiled horn was manufactured in Composite Material Center of CTC 54. In the left photo is the photo of a test, and you can see the frequency is 0.98 to 1.26 GHz, and VSWR is lower than 1.233. And please see the result of insertion loss. And the insertion loss is 0.48 dB. This page is the result of radiation pattern in 0.98 GHz. And this is the result of radiation pattern in 1 GHz. This is the result of radiation pattern in 1.1 GHz. And this is the result of radiation pattern in 1.26 GHz. Two kinds of horns have been manufactured at CTC 54. The first one is on transportation, and the second one is ready for delivery. And we have two two horns. The second horns, the VSWR of second horns reduced from 1.557 to 1.26 because of the optimization of processing technique for horn rhythm. So the second generation horn is better than the first one. Let's review the feature of smooth wall profiled horn. And we can see the size of the horn and the frequency, and the VSWR is lower than 1.3, and the processing cycle is 15 to 20 days. And it's also have good agreement for both simulation and measure pattern. And that's it. Thank you. Thank you, guys.
Que dá o microfone aqui também. Vamos dar esse. É daqui. Okay, so do you have any questions? We just can make some questions here close to the computer, but we are trying to set the microphone, so we'll be able to make questions around the room. Okay, so if not, we would like to say thank you to Dr. Ziqian Zhang. Thank you so much for your time. It was a pleasure to hear from you. So thank you.
Thank you. Thank you. Thank you very much.
So now we can have our next speaker, which is Professor Shulei Shen. So Professor Shulei.
Hello. Hello, everybody. I'm Shirley Chen. I thank for inviting me to give this talk, although unfortunately I could not go to Brazil at this time. May I share my screen?
Sure, please.
Can you see my screen?
Yes. Yes, now it's in the presentation mode.
Maybe I will. Okay, I will just do it like that. Okay, so I will talk about the Tianlai radio telescope. So this is a picture for the Tianlai experiment. So the Tianlai in Chinese means the heavenly sound. So the idea is try to probe the baryon acoustic oscillation, just like Bingo does. And we also try to do intensity mapping. I guess for this audience, I don't need to explain too much, but basically we observe the sky with a low resolution, so that even though we could not resolve individual galaxies, we can still get the map of intensity and recover the power spectrum, and using the BAO as the standard ruler for the cosmological measurements. So based on this, it seems that size of around 100 meters might be the most optimal in terms of the product and the price. But then we will, if we really try to do this intensity mapping experiment, we also have a lot of challenges because the foreground is very, very strong. So on top of the 21 centimeter signal, now here I use the picture made by Jalik, which is for the EOR signal. But even for this mid-right shift 21 centimeter signals, the situation is the same. Basically, we need to achieve a detection of the 21 centimeter signal, which has a raw signal to noise ratio of 10 to the minus 5 because of the presence of the galactic foreground. So in principle, this foreground is smooth. So if we subtract the smooth foreground, we should be able to recover the 21 centimeter signal and use it for the power spectrum measurement. In practice, the instrument response may be not so smooth, and it will introduce complicated apparent foregrounds and need sophisticated processing. So people have been developing various ways to deal with this. For example, the PCA, SVD, and the ICA methods. And more recently, deep learning methods have been applied. But basically, one can achieve something of extracting the signal in the presence of a foreground, which is about 10 to the 2 or 3. So we need to try to kind of first reduce the smoothness, this apparent foreground as much as possible. So here is the Tianlai array. So we actually have 2 arrays. One is what we call the cylinder array, and one is the dish array. So this is basically trying to see which one works better, because the whole experiment is still in the pathfinder stage. So the cylinder array has a large field of view. If you place these 3 cylinders in parallel in the north-south direction, then it will view a sky in this strip going from north to south through the zenith. And as the Earth rotates, one can scan much of the observable sky. And it's relatively cheap. So we currently have 40 meter long of this, but because we have a limited amount of money, so we only have 96 receivers placed on these cylinders, so they only used 12.4 meter in the center section. For the dish array, we have 16 of them, and we have placed them in this concentric circle arrangement. And they are very close to each other and very compact, very dense to achieve a complete UV coverage. And this can be pointed to different directions. But usually we also let them to work in the drift scan. So they have electric motor drives to pointing to directions, but we usually do the drift scan observation. So we have done some forecast using the Fisher matrix method. So basically we predict with the this shades region, it shows that in the ideal case, how much power spectrum measurement precision we can achieve. And these error bars showing that if we make an upgrade, the details I will not discuss here, but if we make an upgrade from the existing one, we could achieve better measurement. And this shows the kind of blow up of the baryon acoustic signal case. And if we can achieve this, we can measure the angular diameter distance, the Hubble expansion rate, and the growth factor like this. And then we can also constrain the dark energy equation of state. But of course, these are all very theoretical, because in reality, we will have complications. Now we decide to look for a good site. So we have run through much of the in many areas in China. So I realized the Bingo people have been also trying to find an ideal site in Brazil. In our case, we finally settled in this Hongliuxia site, which is in the northwest of China in the Xinjiang region, and it's in the Balikun County. So this is a relatively sparsely populated area. So we have the antenna here, and the nearby village is around here. So we have the station house here, and they are connected by an optical fiber cable. And if we want to go there, we need to drive around. So the optical fiber is about 8 kilometers long. And these are the measurements of the radio environments there. when we built the array. So you can see it's very, very clean in most of the bands. In the low frequency bands, of course, the radio wave propagate very long, so very far. So even though nearby there isn't transmitter, but in the lower band you can see still some kind of interference. In more recently, because of deployment of the 5G signal, we now have some kind of interference in the band of observation. So here we shows the this is taken by a drone from above the antenna. So these are the cylinders. These are the dishes, and we have a little room to store some of the tools there. And here is the power supply. And these are the photos of the antennas. This is the block diagram for the system. So the antenna is a dual linear polarization feed, and the signal is amplified by the RNA on board the antenna, and then it uses a 15-meter coaxial cable, which send it to a converter, which convert the electric signal to a optical signal, then using this optical cable sending to the station house, where it is converted back to electric signal. And then we have a bandpass filter, and then it's further amplified and then converted, down converted to the intermediate frequency. And this intermediate frequency signal is then sampled by the ADC and redistributed for cross correlations. So this is the F engine and this is the X engine. And the correlated signal, or what we call the visibility, will be integrated and by this accumulation and then stored on the server. It will be the hard drive that we can ship back to Beijing for further processing. The working frequency is adjustable between 500 and 1500 megahertz. And we have ADCs working at 250 megasample per second. And we use the band filter to control, well, we use the local oscillator to adjust the band to be observed, and use the replaceable 100 megahertz bandpass filter to filter out the outside band noise. And the intermediate frequency is 125 megahertz. And currently we are working on 700 to 800 megahertz with a frequency resolution of 0.122 megahertz. But we plan later on to switch to higher frequency corresponding to lower redshift, so that the signal may be stronger. So these are the cylinders. So for different arrangement, so we have shown what we call the regular cylinder. So regular, we have chosen two different. So on this regular cylinder arrangement, each cylinder has 32 feet, and then we also have their spacing is either 0.4 meter or 0.8 meter. And you can see there are these grating lobes in this arrangement. So we also have this irregular arrangement, in which case we place the 31 cylinders on cylinder 1, and 32 on cylinder 2, and 33 on third cylinder. In this way, the grating lobe is reduced, and currently we are adopting the 0.4 meter spacing. For the dish, we have considered, for example, a square arrangement and the concentric ring arrangement. And here we show how the sampling in the ML space. So the ML is the spherical harmonics. And you can see in the case of the square array, there are these places where the noise is very low, but there are also these high noise regions, very regular ones. Whereas for these spherical ones, the sampling is more uniform within certain range. So we later on, so we basically settled on this design. So we have been using this what they call the M formalism to make images. So the visibility of the measurement of the interferometer array is the cross correlation of a pair of the receivers. Now this is related by the interferometer equation to the sky temperature and the beam response, the primary beam response. And then this is the phase factor for a given direction. So when we integrate L and M, which are the cosines of the angles, we have this visibility. So this basically shows that the visibility is a linear mapping from the sky temperature. And for small area, small sky area, this equation can be reduced to a very simple two-dimensional Fourier transform. Because we are dealing with large scale area, so this Fourier transform cannot work. But we can use the so-called spherical harmonics method, which Richard Shaw first developed, but our group also developed independently. And we decompose, excuse me, we decompose the visibility in the different M modes, and we also decompose the sky temperature and the beam response, the primary beam response. And we found that writing in discrete form, the visibility metric vector is related to the sky temperature coefficients and the beam. And so this is a linear equation, and we have a noise, which is a random. So we can get a least square solution for this using an inversion. Now, in reality, this B matrix cannot be inverted, but we can use the pseudo inverse of the matrix. So for a pseudo inverse means that a matrix cannot itself be inverted, but we can make a singular value decomposition like this, and then we can remove some of the small, smaller modes, and only taking those singular modes with large eigenvalues or singular values, and then we can inverse this. So this is a software processing pipeline we have developed, which is also available on the GitHub. So basically, the input data is first flagged for the RFI, and then we use what a sky source, strong sky source, usually Cygnus A, for calibration. And but Cygnus A transits through our telescope only once during the each day. So at the rest of the time, we try to keep the array instrument phases calibrated by what we call the relative phase calibration, which is basically broadcasting artificially generated noise signal. And then we get the, after this processing, we can get the data, and we check the quality of the data and reject the bad data. And then we can binning them according to the local sidereal time. And finally, we can use the accumulated data to make a map, and then make further processing. So currently, mostly we have been working on the first few steps. So these are the, for example, the RFI masks generated for some data. And here I show the cylinder and the dish visibilities. These are the row visibilities, but you can see, so this is a time, and here I show 6 days of the data, and for each day, this is the frequency. And you can see some of these horizontal lines, which are relatively stable during the night. Here shows the daytime data. So these are basically kind of produced by the cross couplings within the array or other some of the other what we call the correlated noise. So we subtract these unchanging noises. But you can see there are some of these things here. The bar, the vertical lines here. These are actually produced, I think, by the reflection of the moon. But anyway, so we after this processing, we get this data which shows more clearly the fringes in the barometric fringes during the transit of bright sources, and this shows the dish array results. So in all cases, you can see we have a relatively stable response on each day. We can see clearly almost the same pattern, and in fact, we can also see this slightly tilting edge, which shows that the sun is moving across the sky during the different days. So we do this absolute calibration using a formalism based on eigenvalue decomposition. So for each visibility from excuse me, a pair of elements I and j, it should be the proportional to the gain for the I and the j, and also the response of the antenna, and also, of course, the exponential factor due to the phase. And because of the initial, so then we can make if we write this GI like this capital GI like this, we see that this Vij is actually basically proportional to Gi times Gj star. So G is basically an eigenvector of V0. So if we make the eigenvector decomposition, we can get this Gi and the Gjs, especially their phase. So then this can be used to calibrate the instrument phase. So here I show that because we have a number of redundant baselines, so without calibration, even though the redundant baselines, they should have kind of so there this is the real and the imaginary part of the visibility as these are complex numbers. So because their instrument phase are random, so they should be on a circle, and also because they have different amplitudes, if they are perfectly calibrated, they should be a circle. But in fact, the initial case is not. So you can see there's a spread. But after the calibration using our method, we obtain this perfect cross circle, showing we have done proper calibration. We have simulated the beam of the antenna. This is very complicated because the beam phase and the beam's reflector, they have vastly different scales. So we used some special techniques to simulate this. And these are the simulated beam, antenna beam. And we also measured for the antenna beam for the dishes using a drone, unmanned aerial vehicle. So we have been flying these, and these are the measurements we obtain. And you can see we can, during different observations, we can recover very well the antenna response. The black line is the simulation, whereas the red and blue are different measurements. They do not completely agree with the simulation, of course. And this is a comparison of the CAS-A calibration and the drone calibration. So after this, using this relative calibration, which is basically we broadcasting the noise signal and try to use it to determine the phase change of the signal. So after this, we can check whether there's error in the calibration using the closure phase, because if you sum up the three relative phase between three different receivers, you should get 0 if everything is perfectly calibrated. But in fact, you get a kind of a spread of the closure phase, which in our case, so in the amplitude, is at a few percent, and in the phase, it's at about 0.1 reading. So so we kind of think that this well, maybe not 0.1, maybe 0.05 reading. So these are kind of what we get. And we also measure the system temperatures. So here we use the 3 different methods to measure these system temperatures, which are based on the mean value and the variance value. So so you can see in the bottom, we shows the A and the B and the C cylinders, and each for X and Y polarization, and we number the feeds along the cylinder here, and basically the 3 are consistent with each other, although the method 3 generally gets higher value and the method 1 gets lower value. And among the antennas, the one on the east has slightly higher system temperature. So we published this on the Science China. And also for the dish array, we have made the dirty image here. And one problem is that we can see that there are these strong variations in the bandpass. So these are probably produced by either reflections on the antenna or by the cross-coupling between nearby pair of feeds. So one thing we decide to do is to overcome the reflection part. So we have done a delay spectrum analysis for these band passes, and you can see there is this broad peak around 150 nanosecond of delay, which is corresponding to this 4.8 meter reflection. So we basically try to subtract this. But in fact, even after subtracting this, it will not be perfect, but it does reduce the amount of this bandpass variation. This shows that this delay spectrum and the different polarization, well, the receiver and polarization channels, and yeah. Anyway, so we have further done a number of simulations to see how we can improve. So these are actually done for the dish array, is done by our French colleagues, Olivier Pederou and Riza Ansari. They have calculated how the power spectrum measurement is related to the various performance of the antenna, and especially they tried to simulate how observation of either the North Celestial Pole region or a mid-latitude region, how which one will get better results. And basically they think probably the North Celestial Pole region will still be better. So we will for this dish array, we are considering to do this. Basically, we will starting from the center, the North Celestial Pole, but then extending them towards the outside and in concentric rings, so that we can basically survey some area around the Northern Celestial Pole. And our colleagues in the US have used some of their telescopes, small optical telescopes, to conduct a survey of the North Celestial Pole region, because although there have been many large surveys, such as the SDSS optical survey, the North Pole region is usually not surveyed. due to some technical reasons. So basically, they collected the data on the North Pole region galaxy distribution. So we plan to do a cross correlation over there. We ourselves have been more focused on simulation for the cylinder case. So this is a work by my student Kaifeng Yu and our group. And so here he used a sky model and adding 21 centimeter and noise. And then we kind of trying to discover how the variations in the gain and errors in the calibration will affect our result. So here is how we model we basically model the gains as Gaussian processes. And then we chosen the Gaussian process parameters to basically be fitting the observations. And we think if we can calibrate them, maybe if we can achieve a calibration error of 10 to the minus 3 to 10 to the minus 2, then there will be, so then the foreground will still be about 10 to the minus 2 and 10 to the minus 3. But in that case, we can use the blended foreground removal programs such as the SVD, SAA, or deep learning to try to recover the 21 centimeter signal. So here we have done the simulation of the absolute calibration and the relative calibration. I do not have time to go into too much detail here, but I would say that the result is different from what we originally thought. So we originally thought that this relative calibration using the noise source will generate a lot of error. But in fact, our simulation showed that the relative calibration is quite precise. Our main source of calibration error is coming from the absolute calibration, which we use the Cygnus A observation to calibrate. Now, the reason for this is not that the noise, but because in this calibration algorithm, we have assumed the sky is dominated by the Cygnus A, but in fact, this is not. The other part contributes to this. So we have to think how to more precisely model the sky in order to do this calibration. Then we studied the imaging process. So this is the dirty map, and this is the reconstructed map. Now you can see some of these blue horizontal bars. These are basically because there are very bright sources, Cygnus A and the CAS A, and we try to subtract the average so that we achieve a zero average. So in this case, the sky on the same latitude becomes negative. But then you can also see that there are these large side lobes due to imperfect calibration. We can use these, so this multiplying this B star B's inverse is equivalent to deconvolution. So this is basically the reconstructed map. So in the reconstructed map, the side lobe is reduced, but not completely eliminated. So here, these ones, we basically assume sky is only having a few strong point sources for the simple case. Now next, we simulate a more realistic case of sky model. And here we found that depending on the truncation threshold, whether epsilon equals 10 to the minus 3 or 10 to the minus 5, we get different results. Now, of course, if you have a very small truncation threshold, you lose very little information, then you can do a better reconstruction. But with the presence of strong noise, sometimes this doesn't work. So you have to settle to a larger threshold. For this larger threshold, you can see there are these what we call comb-like structures the horizontal structures around the brighter part of the sky. And if we calculate the input map, subtract the difference between input and the reconstruction map, you can see the clearly being centered here. Okay, so we also do angular power spectrum analysis. This is the reconstructed CL, and this is what I think the correlation coefficients. Basically, we cross-correlate the reconstruction CL to the original CL and divided by the input. And what we found is that at L below 200, we can relatively well recover the original CLs. So the coefficients is basically 1. But then above 200, or more precisely 195, there is a drop in the correlation coefficients, showing we cannot completely recover the spherical harmonic modes. We have studied this, showing that this scale corresponding to the north-south scale, which is currently only only 12.4 meters. The longest baseline is 12.4 meters in the north-south. Well, in the east-west, we have about 30 meters long baseline. So here, due to this insufficient resolution, we are losing the information. And we also studied the impact of calibration. So in fact, the result is a little bit better than we thought. So we think currently the calibration doesn't introduce too much error. So most of the most of the error is not from the noise or the calibration, but in fact from insufficient sampling of the UV space, and so that the theoretical reconstruction isn't completely satisfactory. So we are thinking to reconfigure the array so that maybe we extend it a little bit in the north-south to have a better sample on the north-south direction. These are the expected configuration, so that we can measure up to 300 or even 400 of L. We also tried instead of the usual TSVD method or the Moore-Penrose method, we also tried the Tikhonov regularization, which instead of cutting off all modes below a certain signal-to-noise ratio, we introduce a gradual separation. So in this case, you can see in this case, the comb-like structure is less obvious because we do not sharply cut off this. Well, I'm probably running out of time, but anyway, let me show that we also try to look for the FRBs, because during this service, of course, we will have a lot of sky area covered, and we can search for FRB. And we have a digital beam forming designed so that we adding the voltage signal of different receivers in phase. With compensating phase. By varying this compensating phase, we can make the digital beam pointing to any direction of the sky. And we currently have installed on both the dish array and the cylinder array a backend, a digital backend. And in this case, we can in the dish array we form 32 beams, and in the cylinder array 96 beams. And after forming the beam, we can try to search. We can do d-dispersion and FRB search. So in last year, in April of 2022, the cylinder discovered one FRB burst. The DM is about 208, and the peak the peak flux, if it is at the center of our sensitivity, is about 128 Jansky. If it's outside the center of the sensitivity, maybe it's even higher. So anyway, and for the dish array, we have been trying to observe a repeat FRB, this particular FRB, and on November last year, we also detected one burst. In this year, we have some kind of renovation for the site, so we haven't observed much, but we plan to resume this observation very soon. And we are thinking to adding some outtriggers far away and trying to cross-correlate so that we can better determine the location of the FRB. So we have chosen a number of sites. So our original cylinders are here inside A, and we plan to build 2 more smaller cylinders at position B and C, and trying to using them to triangulate the position of FRB if we detect FRB. Okay, so let me conclude here. So I think 21 centimeter cosmology has a great potential, but require very high precision and sophisticated analysis. So our Tianlai project is currently still a pathfinder, but right now it works as an experiment to learn about the required key techniques. So our current version have small antennas and limited in sensitivity. We can already learn many valuable lessons about real-world data analysis, and there is a good opportunity for FRB search. We welcome domestic and international collaborations, and especially we look forward to collaborate with the Bingo collaboration. Thank you very much.
Thank you so much, Professor Shirley. Please, if you have any questions, I guess you need to come here because. Hello.
Hello.
Hello. Hi.
Hi.
Hi. Hi, Professor Shirley.
Yes.
So I have 2 questions. First, is there any event that you could of FRB event that you could see with both the cylinder and the dish? Or
I turned it off. In principle, yes, because but the chance is very small, because the cylinders have a larger field of view, and is in the narrow strip along the north and the south direction, and we also plan to pointing the dishes. For example, in a large chunk of time, we'll be pointing toward either the north celestial pole or near north celestial pole. So they are in the same field of view. So what you said, yes, there is some small chance. But I have to admit that in our case, either both of these arrays, the rate of detection is relatively low. So depending on the assumptions, we probably get either 1 or 0.5 rate event per month. So I think the chance is not high.
yes, I see. And a second question would be, what is the length of the baseline for these outriggers?
So we currently place them around 10 kilometers. So of course we could have a higher precision if we locate them even further away. But we are limited in the budget, so we decided to put them around 10 kilometers, so that in the end they achieve perhaps arc-minute precision in the location.
I see. And as a last question from my part is for the reconstruction of the beam pattern, you're doing simulation. have you ever tried to maybe use some drone or some other technique to have it observed experimentally instead of simulation?
We have used the drone to measure the dish, one of the dish. This experiment is done in 2018. The paper is published in 2021, but it's only because the paper has a very long publication period. But the work is done in 2018, and we measured it successfully. And we also plan to do it for the cylinder. But for the cylinder, it's harder because they have a larger aperture. So in order to be in the far field, we need to fly to about I think about 2,000 meters. And so that needs a larger drone, and also need to apply for the space, to apply for the airspace. And so in fact, we also plan to do that, but then we are hit by this pandemic. So we couldn't really actually doing things during the pandemic. So we didn't do much. But we plan to resume this work maybe next year.
Okay, thanks a lot. Any other questions? Please come.
Hi.
Hi, Jiajun.
Hey, Sean.
Nice to see you here.
Nice to see you here. My question is about the data center. I just noticed that in your talk you said that you transfer the data from the site through a fiber by 8 kilometers to the near location, and storing some of the hard disks there, and then send those hard disks from time to time to Beijing for the further data analysis, right?
Yes.
And then in this way, so in the local data center, do you know how much storage is in the local data center, and what frequency you send the data back to Beijing?
Well, we have something like I forgot exact number, but on the order of 100 or 200 terabyte for the hard drive on site. In fact, we didn't do too much shipping because in the past few years, there had been a lot of hardware breakdown. So in those cases, we didn't actually take data. So, but if we are running full time, then probably we need to ship the hard drive every month. But in reality, we didn't.
Okay. And so the local data center there, do they equipped with sufficient computation power so that they can deal with the data on site, or the local data center itself is just saving data, and we need to do any kind of data analysis after sending those things back to Beijing?
We originally, when building this, we are very limited in budget, so we do not have the extra computing power for doing computing there. The system there is purely for doing real-time processing, and so we have to do it backwards. So I have been thinking that to adding some GPUs there, so that we can actually doing the processing there, at least maybe doing the calibration processing there. So then if we have done the calibration processing there, we can save a lot of computing, because for us, the computing is, we have to pay to do the computing. It's unlike, for example, in Shanghai Observatory, you have this proto machine, which practically are free right now, but we do not have this. We have to either ask someone to do us a favor, or actually pay for the processing. So if we can do the GPU processing there, then it would save us a lot of money. But in fact, this hasn't been done yet. So so far it's not so perfect.
Okay, thanks. Okay, so if you don't have any more questions, let's thank again Professor Xue Lei.
Thank you. Bye.
Thank you so much, Professor. It was amazing.
But
Thank you.
just follow, really, the also is here. Should say, end of week, the also is.
Yes, we have Professor Asu and Professor Bean here too. So. Okay, so the next speaker now is Professor Peng Wang. So Professor Wang, thank you so much for your time and for being here with us. So feel free to start your talk.
Sorry for my mute. Thank you for this opportunity. I can share recent fast discoveries on the pulsar FRB and the related studies using the FAST. I'm Pei Wang from NOC on behalf of the FAST calibration. My talk is the FAST perspective on the dynamic universe. Okay, the FAST telescope is a 500-meter aperture small-scale radio telescope. The FAST is located in the Guizhou province. Many of the hills around the FAST single-dish telescope. The overall cost less than the $200 million. The design, the frequency range is a few megahertz and to the 3 gigahertz. Now the FAST equip airband 19 beam receiver with the frequency from the 1 gigahertz to the 1.5 gigahertz, and the angular resolution is about 2.9 arcminutes per beam. And now because that the FAST telescope have equipped with the airband 19 beam receiver, so the field of view about nearly 26 arcminutes for the field of view, and the sky coverage and for the FAST is from the definition from the minus 14 degree and to the 36 degree, and again, and the sensitivity is respective is 16 Kelvin per Gansky, and for the single pulse search, the fluence, the limit is about 17 millidansky multiplying the millisecond. This is the 7 sigma level. So we can see, and this is the photo, and for this is the control room, and this is the reflector, and this is the building of the observatory, and this is the reflector and the overview of the FAST. So and we can see here this FAST is located in the around these mountains. Sorry. The FAST starting construction from the 2011, and after 5 years construction, it's 2016. The FAST have the first light. From the 2017 and to the 2019, is a FAST engineer commissioning phase, and from the 2020. The FAST have the full scientific operation and in the Guizhou, and so I fully and enjoy and I fully join in that early stage of the commissioning phase and the fully working with scientific operation. So we can see here, this is a cartoon that like the coming Christmas Day, and that's a gift and for the from the battery and the pulsars and the black hole and other FRB transit source and in the sky and FAST and can have the great sensitivity and can detect some of these for the observation time, and in the fact about 5,000 hours per year, and includes 2,000 hour opening time and for the proposal call for per year. In the fast observation, and I have here now have the 5 key project, just like the pulsar service, FRB service, and the H1 mappings, and for the M31 galaxies, and all the data will release after 1 year. And we can image all the scientific targets and in the bottom of the cartoon. And we can see here have the 3 dimension, is the time, space, and the frequency, and from the 1 to 3 gigahertz. We can see here this is the galaxies, and this is gravitational waves, and is molecular cloud, and here this is the neutron stars or the pulsars. Here this is measures located in some of the specialized frequency. We also can compare with the size with the different international single dish telescope, just like here. This is Parkes in Australia, and Effensberg GBT 100 meters. And here this is Arecibo, and here is the 500 meter the fast. But the fast the effective collected the dish is about 300 meter. Because, and we can see the whole of the reading is 500 meter, but the effect area, the effective area is 300 meters. It can move from the north to the south during that observation. So we can see here is the motivation and for the pulsar and the FRB search. So we can see that the pulsar size is divided into the 2 steps. The first step is to search, expand the simple set of the pulsar studies. Here we know more than 300 and till now more than 3,500 pulsars have been discovered, and we can expect the breakthrough, the discoveries from the certainly come as the service go on. We can see the left panel, and here this is the timeline from the first pulsar discovery in the 1967. We can see the first millisecond pulsar, and the first millisecond pulsar in the global cluster, and the first extra solar planet, and the first double pulsars, and the first FRB, and the first radio magnetar, and a lot of the new discoveries from the pulsar search. So in the fast perspective, we just to stone the single pulse and the baseband data, and for the single dish, and to apply to data processing, and to find the periodical signals and the highly dispersed the single pulse, and in the time domain, and also in the Fourier domain, and to search that the pulsars and the FRBs. We can see the red panel is the map of the distribution of the various type of the radio transients. Each point shows a transient here, reflecting the huge dynamic time scale of the universe from here. This is the timeline, just reflecting the huge dynamic time scale of the universe from here. This is the nanosecond and to the billion years, and the vector x is the luminosity or the energy. The pulsars and the FRB timescale here. This is the time. This is the group of the pulsars, and this group is indicate the FRBs and the repeating FRBs. We can see the pulsars as and the FRB, the timescale also just like the from millisecond and to the few of the second. The time scale is quite similar, but have the huge, large, but the very large difference in the energy of the luminosities. We can see here some of the red dots are discovering hundreds of the new pulsars and a dozen of the new FRBs by the FAST. Based on the FAST sensitivity, we also expect to detect the FRBs at very high the red shift and to reveal of the 11 billion years before the evolution of the universe. And we can see the limit for the radiometer estimation. The FAST can be detect the red shift, the Z, the 10 of the red shift of the FRBs. Now FAST is carrying the two surveys. The one is the craft survey, and another is the GPPS. The two surveys have the very different strategies. The craft survey is a commensal radio drift scan FAST survey. Based on the drift scan, this is more efficient for scanning all the FAST sky region, but the integration time is less than that another survey GPPS, because the GPPS is focused on that the deep integration and the grading survey. The GPPS is a galactic plane grading pulsar survey. The focus on the galactic plane and to use the 4-point grading configuration and to coverage the galactic plane. We can see here have the 4 colors. Each of the colors is one pointing for the 19 beams. And so combine the 4 pointing of the 90 beams to use the FAST airband 90 beam receiver can coverage the whole region in the galactic plane. And each of the point have the 5 minutes integration time, and for the record the 8-bit, 8-byte the single pulse search. To record the 8-byte the single pulse date and offline and to process. Very similar and to the craft survey, and the craft survey that record the data stream in the drift scan towards one of the destination each day. So the two surveys is the most important the pulsar and the FRB related surveys for the FAST. And we can see here this is a drift scan of the FAST survey, and towards that is the torus molecular mapping. And here the B panel, and is the discovery of the FRB discovered from the craft survey. And C is the H1 imaging of the during that drift scan from the CRAFTS survey, we can to mapping that the intensity of the H1 spatial line and mapping for the observed sky region. Okay, and this is the details of the CRAFTS survey, and this project is led by Professor D. Li. The spatial lines of the CRAFTS survey is the commensal. The commensal means the H1 mapping and the POSA and the FRP survey is simultaneous and to carry out. We can see here this is a map. This is in the galactic plane, and we can see about 20% sky coverage have been carried out, and we can see that the red dots and the blue region, is have covered the sky region in the last year and this year. And the red dots are the new POSA discoveries and from the CRAFTS surveys. So now from the CRAFTS survey have discovered and confirmed more than 180 POSAs from this project and include more than 40 millisecond POSA and more than 20 binary system, and include one of the double neutral stars and about discovery about 30 R-rights and about the two POSA with very specialized narrowband emission and with very different spectral index from the POSA emission. And the confirmed all the POSA discoveries can be found in the this web page is the CRAFTS POSA catalog. And all the published the paper and can be found and in the ScienceDB FastTraw. And this is the web page we can see to use this web link. We can see here, this is trend and the discovery number, and through that timeline, and we can see the different color is a different type of the pulsars. Some of the pulsars is very special, and for example, and we can see here some of the color lines is intimate death line and for the pulsars, and we can see some dots are below of the speed up the lines that indicate here this is a very strange, the pulsar is very, maybe that is very old and hard to emit that the radio position in this state, but this is they are rare samples from the pulsar studies, and so we just to monitoring and to timing and this pulsar and to review that is the nature of the radio emission. We can see here this is the first pulsar discovery by the FAST, and we can see from this panel and the right panel are the first two pulsars discovered in the 2017. Till now, from the CRAFTS and the GPPS and the TOOP surveys now have discovered more than 750 new pulsars here. And for some of the specialized pulsars, the FAST will monitoring and to do the pulsar timing and towards these targets. And for example, and we have confirmed that one of the double neutral stars in the discoveries, and also review the two of the millisecond pulsar and the Black Widow, the binary systems have we can see here just like the image. And here this is the arrival time and the arrival time in the eclipse during the eclipse the phase. We can see here the have the large of the residue. The large of the residue that comes from that eclipse and the wind nebula from that accompanying of the pulsars. So that is have published that the several of the papers to study the depolarization and the plasma lensing effect before and after the eclipse. And here, this is the panel. It's the first millisecond pulsar discovery, and this is the pulsar that is consistent with gamma ray associated source in the Fermi light dataset. And so this is one of the extremely radio fine millisecond pulsar from that till now, and this is a joint observation and from the Fermi light and combine the fast observation and can make this discovery. And we can see here this is the bottom of the panel. This is orbital. This is the orbital phase during the observation. After the regression, and we can see here this is a vertical line. The vertical line is that the pulsar signals from the binary pulsar. And this is the binary pulsar is also have the gamma ray emission and can be found and from the Fermi light, but discovered by the fast observations. So we can compare this is a pulse profile from the gamma rays, and this is from the radio profile, and we can further to make that the pulsar timing and to make the phase offset. And to gain and we can to get that important information and from between that phase offset. In addition, radio counterpart detection was carried out for the null pulsar. That is the null pulsar is the radio quiet gamma ray pulsars. The radio pulsation and from the radio quiet gamma ray pulsar J0357, that the gamma ray pulsar located in the torus, a big bubble. That is the big bubble. We can see this is the image of the torus molecular cloud. In the center of that, the torus molecular cloud have a no gamma ray pulsar in here, but have the radio quiet. In the 2017, and the fast have the observation and to use the half an hour of the integration time and to detect that radio counterpart and for this gamma ray pulsar. And the rotation period is 0.4 second. Is very consistent with the Fermi gamma ray pulsar detection result. Before that, the fast detection, no radio pulse be detected, and the observation was successful, and that the observation was successful confirmed by the RSAble, and in the 2018. So what's the meaning and why this is very important and for the discoveries? Because that the torus, the molecular cloud is distance of about 160 PC is very closed. The star form is very close the nearby star forming region, and if the pulsar is located in, it will be the closest the pulsar, and that the pulsar potentially involved in the evolutionary process of the molecular cloud star formation. However, and from the detection dispersion measure, and we can to use that the electronic galactic model and to estimate that the distance is about 1 kpc. That is much higher than the torus molecular distance. So have another possibility that is that the pulsar may also non-interaction with the torus and potentially be a highest the velocity of the purple motion pulsar. So either of the outcome is very interesting, and either in that is the nearest nearby pulsars, or that is the highest safe velocity purple motion pulsars. For the fast radio burst study field, the FAST have discovered more than 13 new FRBs through that two surveys. The crafts have discovered about 8 new FRBs, and the GPPS have the 5 FRB detected. We can see here only one of the FRB 190520 is the repeating FRB detected from the crafts, and that discover made by the Dr. Chen Huiniu, and I will show these details later. Detector and the other FRBs seems on-off FRBs, and the flux and the luminosities of the new FRBs have much lower than the chime FRBs. We can see here in this panel. This is the published FRB from discovered from the crafts. The vector axis is the fluence. And here this is axis dispersion measure, and we can see new published and new discoveries FRB in the corner of the whole of the distributions, and so that indicates the luminosity or the flux density is very low compared that have been published from the chime collaborations, and also the exact the DM is higher than the other FRBs. That means that is more distance compared with other chime discoveries. From the 2020 to now, the FAST carry out 5 of the key science project observations about the more than 400 PI objects from more than 30 countries all over the world, and more than 300 journal articles published, and include some of the Nature paper and the Science paper, and just focusing on the repeating and just focus on the repeating the FRB monitoring, and from the FAST have published 9 of the Nature paper and 2 of the Science paper till now. So now from now we can focusing on the fast follow-up for the repeating FRBs, and this is have the most advantage and for the fast observations. We have the two main strategies. The first is we want to know what is the central engine of the FRB, and the second question is what's the environment of the FRB origin. The first question and may be solved by the birth population statistics. That is includes the time evolution and the time period, and also includes that the energy distributions and the birth rate distributions and the period search, and this is statistical phasers can reveal what is the FRB central engine. And for the another the question, and what is the environment of the FRB origin? The environment can be reflected by the either birth or the PRS, the evolutions. We can see here now have the two of the repeating FRBs, that is the FRB 121102 and the FRB 190520. That the two of the repeating FRB have the persistent radio source consistent with that the FRB source, and so monitoring that the time evolution of the PRS for that the flux and the rotation measure and the spectral index for the PRS, that is important information and to reveal that the environment and its evolution. So, and we can see this is the first repeating FRB 121102. The 121102 is the first FRB for the localization, and the repeating birth and from the 121102 bring us some basic insights into the origin mechanism of the FRB and their environment. So this source is very is a good entry point. I will focus on the time evolution story of this source to demolish two parts. We can see in the 2019, in the year of the 2019, is the further commissioning. In the further commissioning phase, the further detects a large number of the high signal-to-noise ratio repeating pulses, and this is the pulses have multiple types of the flux, have the complex time and frequency structures, data like this. The fast because have the most sensitive and for the detection for the single pulse, so the fast largely expanded low energy detection ability. After careful calibration and the single pulse blind search, from the FRB 121102 have a clearly structure of the birth rate. We can see here. This is a pink. This is a phasor pink energy, and this pink energy around the detection threshold of the irreversible. But after our simulation on the fast detection, we can see this is a red dashed line from the fast detection, and this is indicates 90% completeness threshold. Above upon this completeness threshold, here we can see here this is the pink above this line, and this is nearly a completeness. And from this pink and to this dashed line, and we can see that the birth rate will drop off. That is the drop off is real for this the nature. Because here this is a solid that is a threshold, and so the FRB 1102 have a complex energy distribution, and this is can be better described as a log normal and plus a Cauchy bimodal functions and to describe. And the solid black line, and we can here there is a power law log n visuals the log s. Here seems to be artificial detection bias in the low energy region. Let's see how the bimodal is generated. The bimodal, and we can see here this is a contour. This is a contour map. The bimodal of the birth rate comes from that the first 10 days. Then the high energy components disappeared. Here, this is a clear time evolution behavior, and this may shed light on the different types of the century engine. This result was published in the Nature in the 2021. For another, the red panel is a DM dispersion measure time evolution, and this is a timeline during that more than 10 years monitoring. We can see the DM value slightly increase year by year from that slope of the 0.85 per year, but the DM but the dispersion measure start to decrease quickly, leading to an overall trading of the non-linear time evolution over the time. This makes the supernova remnant diffusion model fails, and campaigning that the decay pattern of the rotation measure and the evolution trait of the DM could be valuable insight into the origin of the environment around the FRBs. For example, that RM decay combined with the DM non-linear time evolution, and we can include that is not become from that SNR scenarios, and that is can be possible from the BE massive star binaries, and this is the result and will be submitted soon. And we artistic the result with the style of the ancient Chinese painting, a river of the this is a river, the river of the birth, and based on the real pulse profile of the FRB 121102, follow from its host galaxies into the fast telescope, and the mountains are based on the birth count and the energy distributions of the source, and mimicking that painting vast land by the Wang Ximeng from the Song Dynastics. As you may remember, that the FRB 190520 is the only one repeating FRB detected from the CRAFTS survey. We performed the multi-wavelength observations. The source located with a compact persistent radio source in a star formation dwarf galaxies is redshift Z of 0.2 and have the large DM distribution from its host galaxies. Hence, that the source deviate far from that prediction of the Marquardt relation. Here, this is the this source, and we can see this is the prediction of the Marquardt relation. That indicates this is a very special source and have the very dense plasma environment around this source. That is a very important information from the environment of the FRB origin. We then systematic summarize the polarization properties of the repeating FRBs and found that they have the unique pattern of that the pattern is a high polarization in the high frequency band is very high, and the low polarization in the low frequency band. And this pattern and allow us to proposal for mechanics and to cause this uniform morphenomenon. That is the signal from the active repeating burst pass through a complex magnitude and magnetized the plasma environment and generating the multipass structure and generating the multipass scattering, and we can determine the state of the repeating FRBs by measure that the sigma RM, and the result have been published in the Science this year. And accompanying the further radio detection and the optical multiwavelength observations, we further studied the several repeating FRBs. For the left panel, this is the active repeating FRB, and this panel is from the further detection, and with polarization collaboration, we can see here this is the red dots at the PA angle, and we can see during that the position, the PA angle change have the variance, have the different value, and the value and between that position have the large variance. So that is the PA swing consistent with the pulsars magnitude. That is with the pulsars emission mechanics origin. And for another of the left of the right panel, and this is based on the rotation measure detection from the 2011-2024 this source. In this during that detection seasons, we have detected more than 1,800 bursts from the further detection, and the area of the burst have measured for the RM, and we can see here this is the red line is the RM tempo evolution. That is the RM just down and up in the times in very short time scale. That provides the evidence of the complex and dynamical evolution environment of the FRB origin. And this paper also published in the Nature. Finally,
Professor,
sorry?
Oh, okay, sorry. I was saying that we are a little bit late of time, so I'm so sorry, but if you could finish your talk.
Okay.
Please.
Sorry for that
Okay.
delay. And this is the last
No, there's no
page.
problem.
Yeah. Okay. Finally, this is the last page and for my slides, and this is a typical magnetar radio emission as a link between the pulsars and the FRBs. And this is to be submitted to the Nature Astronomy. And usually the magnetar radio emission spectral indicates that the spectral index are flattened. This is SGR, the 1935, has the untypical narrow bandwidth radio pulsar emission. And we can see here, and this is a very narrow band and very similar like the FRB repeating FRBs. The further radio detection combined with the NASA and the SWIFT X-ray observations for the first time found the X-ray hardness in the radio emission window inside and outside to the different models. This is will help us and to further understand the magnetar radiation mechanics as a link between the pulsar and the FRBs. So now we have the summary, and up to now the FAST have discovered more than 750 new pulsars and 17 new FRBs through the two of the FAST surveys. Due to the limit of the field of view, the FAST FRB survey is inefficient, and the sensitivity is the FAST most advantage for detecting faint and distant burst. The FAST have the good performance in the polarization measurement and provide a base and for studying that the radiation mechanics. Okay, I study on the pulsars and the FRB problem continue and to be solved, and the new one arise, similarly chaotic, but also fantastic and to the explore. The FAST will keep searching and try to insight into the pulsar FRBs and the evolution of the dynamic universe. I also hope to promote the international collaboration between that FAST and the BINGO, and to join to expand these active new frontiers in astronomy. The best is yet to come. Thanks.
Okay, thank you. Thank you. Thank you so much. So I guess we will need to skip the questions, but we can send some questions for you from people here in the room, and also other people from the collaboration. So thank you again, Professor Peng Wang. So
thank you.
Now, okay, thank you. Okay. So now I would like to call Dr. Yu Sang for his talk.
We can, okay, I think Yu Sang is on.
Hello?
Hello.
So should I start now or there is a break?
Oh yes, I'm sorry, but we had a small break. Would you like to have a break, a little break, 5 minutes break? Okay, so let's have a 10 minutes break. Sorry, Yu Sang, and then we can start. Okay.
10 minutes. Okay.
Okay.
10 minutes sharp.
Yeah. Ok, pessoal, podemos começar? Ok, Yusan,
Hello,
thank you.
can
Okay,
you
thank you. We are here.
can you
Yes, we are
see
listening to you.
my slide?
Yes, we can see. It's very good.
Okay, thank you.
So thank you so much for your time. Sorry for the because we're a little bit late, but you may start. So please.
Okay, so I have 30 minutes, right?
Yes.
Yes.
Okay.
30 minutes in total, but
Okay, I know.
That's
I will try to control the time.
okay.
Okay. Okay, thank you. Hello everyone. My name is Yu Sang, and I'm from Yangzhou University. And thanks the organizer, thanks the committee to give me the opportunity to introduce my work. And I'm a member of Bingo Collaboration, and today I will talk one of my work related to Bingo, that is forecast on the primordial non-Gaussian entity from the 21 intensity mapping. Okay, so first is the motivation. So why do we consider to study the primordial non-Gaussian entity? That is because everything in current universe is coming from the quantum fluctuations of inflation. So we are observing CMB larger scale structure, 21 centimeter from the neutron hydrogen. And the primordial fluctuations give a seed to the structure formation in the little universe. So if the fluctuations are Gaussian, actually there are some assumptions. The first one is in the early universe, the inflation must be a single field model. And the second one is the kinetic term of this scalar field must be canonic. And the third one is the potential of the inflating must be smooth so that the inflating could slowly roll down to the bottom of the potential. So this condition is actually can be satisfied by a lot of models. So I list the name in the bottom. And if we can measure primordial non-Gaussian entity signal, that means that we can root out the largest class of inflation model I have shown in the last slide. And it can reveal other non-standard models that can predicting large non-Gaussian entity, such as the multi-field inflation, K-instance or DBI, or the Covenant scenario, or there must be exotic, there must exist some exotic mechanism like the preheating after inflation. Okay, so from the observational side, besides the power spectrum, there are more information that could be provided by the base spectrum because the non-Gaussian entity is a signature of the nonlinear. So actually the non-Gaussian entity can be constrained using the CMB anisotropy or the large scale structure. And when we observed a map from the sky, actually we don't know where this non-Gaussian entity signal comes from, because it could be the primordial, like what I'm studying here. or it could be from the late universe, like the nonlinear growth of structure, or this non-Gaussian signal could be the foreground noise. So to study the primordial non-Gaussian entity, that could give a template for the primordial signal and will be helpful to the observation. Okay, then how do we describe the primordial non-Gaussian entity? We use a quantity called the base spectrum. The base spectrum is a counterpart of the three-point function in the Fourier space. Here is this angle bracket means the ensemble average, and this Dirac function, Dirac delta function gives the triangle condition. This condition requires that the wave factors of 3K must be close to form a triangle. And that means that all the length of this K is inside this volume shown in the figure. So the base spectrum B phi is a function of the magnitude of the K1, K2, and K3. So next I will talk about the shape of this primordial non-Gaussian entity. This is actually is the different triangle formed by the magnitude of the K1, K2, and K3. The first one is local or squeezed, that the K1 and K2 are close and much larger than the third one, K3. This can be appear in this model of multi-field and Covenant. And the second is equilateral. These 3K are equal. And also the third one and the fourth one, I will not talk too much details. So this different triangle means that the base spectrum will have peaks when the triangle is satisfied. And we can show in the next slide. So the most studied case is the called the local model. And in this model, the K3 is much smaller than the K1 and K2. So the K3 actually is corresponding to a very, because it's K3 is small, so it's corresponding to a large scale. That is a super horizon. So this model actually is motivated by some non-linearity that's outside the horizon during the inflation. And this large scale will have an influence on small scale inside of the horizon, that is the K1 and K2. So this model is will appear in the multi-field models. And in this local shape, the field can be divided into two parts. The first part is the linear part, is a Gaussian field. And the second part is a non-Gaussian part. It can be written in this form with this FNL is the amplitude. So when we are talking about constrain the primordial non-Gaussian entity, indeed, actually, we are constrained this amplitude, this parameter, FNL. Okay. When we transform this phi into the K space, in the Fourier space, and we can get the base spectrum of local form, it can be written in the product of two power spectrum and has the permutations over the K1, K2, and K3. So here we can show exactly that for the local shape, the base spectrum have a peak here, here. So here actually means that this triangle is satisfied that K1 and K2 are equal and much larger than the K3. And besides the peak, in the other area, the base spectrum is small. Okay, and for the other shape of the primordial non-Gaussian entity, like the equilateral or flattened, we can also write the base spectral form, and we can also plot the figure of their magnitude. Okay, and before we move to 21 centimeter, I would like to introduce the current tiniest constraints that are from the Planck CMB. So the technique we use for 21 centimeter is very similar to the CMB. Very similar to CMB. The basic idea is that if the primordial perturbation is non-Gaussian, then it has a specific shape, then there will be a signature inside the map. And from the map, we can calculate the base spectrum and use it to constrain the amplitude of the non-Gaussian. Here I list the result from the Planck paper, and it has different. It shows for different shape, local, equilateral, and orthogonal, and use different map. And we can actually say that for the local shape, the sigma could be like around 5, and compared to the Planck 2013, the result is better a little bit. Okay, so now we can know that the best constraints from current experiment is around this 5. So next we can move to 21 centimeter. So the a brief introduction is that this 21 centimeter line is the hyperfine transition of hydrogen atom. So there are 2 states of the alignment of the electron and the proton, and the energy of these two align is different. So if this atom changes from one state to the other, there will be the energy will be released or observed by the photons, and the frequency is 1042 megahertz, and corresponding to a wavelength of 21 centimeter. And if this photon is far away in the universe, then the observed wavelength will be redshift. Using telescope, we can detect the fluctuations of the brightness of the 21 centimeter. So it could be approximated by this equation, and it can contribute in 2 parts. The first part is from the astrophysics, and the second part is here showing the red is in the cosmology part. And the key point in the astrophysical part is here the contrast between the 21 centimeter spin temperature and the CMB temperature. So this will influence, will decide whether we will see a positive fluctuations or negative fluctuations. And in the cosmology part, it's related. In the cosmology part, is related to the cosmology parameter omega b. Is very.
Bom dia.
And the Hubble parameters. Okay. Next, I will talk about the 21 centimeter intensity mapping technique. So the traditional way to observe large scale structure is to use the large redshift survey, and this will give, like in the figure here shows, this will give the position and the redshift of a large number of galaxies. And the galaxy are used as the tracer of the underlying matter distribution. So this method actually have been successfully used in optical band. But in the radio band, the nature tracer of matter is 21 centimeter line from the neutral hydrogen. But if we measure each galaxy individually, it is expensive and not efficient to mapping all the cosmological volume. So we can use the intensity mapping technique to measure the intensity of the H1 fluctuations. And the intensity mapping is using a little bit relatively larger beam on the sky. For example, use 1 degree beam, and this beam can contain a lot of galaxy. You can see in this red circle, it contain a lot of galaxy, and similar to CMB, but have more information because CMB only have one map at this redshift around 1 subnet. But for the intensity mapping, we have it's tomography. We can measure at different redshift. Intensity mapping can be used as the mass tracer to proving the distortions in the redshift space, and also it has other advantages. Okay, so after the introduction of non-Gaussian entity and 21 centimeter intensity mapping, now we can move to the how to constrain or how the non-Gaussian entity will appear in the 21 centimeter bit spectrum. It will have a little bit mass, but I will try to give a simple introduction. So we can observe this brightness temperature of the 21 centimeter and use the harmonic spherical function to expand the coefficients is the ALM. And the full base spectrum is an ensemble of 3 coefficients ALM at different redshift. So it can be right in this form. It's a little bit complicated, but we can see that it actually includes 2 parts. The second part here is an integral over 3 spherical harmonic function. And the rest part actually include all the physical information. We present use a B. And this mass function is called Gantt integral. And all the physical information is inside this reduced base spectrum. To compare with the observation, we are average over the M and have a weight. This is very similar to the power spectrum. For power spectrum, we are also sum over the M. But for here, we will have this factor as the weight. Okay. So next, we need to calculate for the local shape and for the equilateral and orthogonal shape, how they will appear in the base spectrum. And we can use the base spectrum and calculate the integration over 3K and over the comoving distance to get this reduced base spectrum. And for convenient, we can divide all the K, 3K into 3 different functions. Each function is an integration over the K. So here we define the 2 functions, alpha and beta. This technique is widely used in the CMB calculation. And also for the equilateral shape, using this base spectrum, we can also calculation the reduced base spectrum. And the same for the orthogonal. Okay, here is all the theoretical formula. And next, we need to consider actually is inside what is this delta. This delta is transfer function. It has all the information of how these perturbations are involved from the primordial to the latent universe. And here I write out the full form, but actually the dominant term is the first 2 is for the fluctuation of the density and the ISD effect. Here I show the result of the calculation of the base spectrum for the alpha parameter, alpha function and the beta function. Because of this Bessel function, it has oscillations over this x-axis is the comoving distance. And for this beta function, it's a very sharp peak. But if you zoom in, you can see that it also has some oscillations, very a lot of oscillations when you zoom in. And use alpha and beta, we can calculate the base spectrum from the 20 nanometer. This is from theory, from the formula I have shown before. So here I show for the redshift Z1 equal to Z2 equal to Z3 and equal to 1. And for all the L1, L2, L3 are equal. Next is we want to forecast. We want to use this base spectrum calculate from theory to see how to what will be the constraint FNL from the experiment. So we use the Fisher matrix techniques. And the Fisher matrix technique for the base spectrum is shown in this, use the first equation. And here for this CL, we consider both signal and noise. Because here we are want to constrain the FNL. So FNL, this parameter actually is proportional to the other part in the base spectrum. So that means this partial B, partial FNL can be equal to this base spectrum when the FNL equal to 1. So we finally, we have used 2 methods. The first method is shown in the first 2 equations, and the second method is in the third equation. The results are the same, but the second term will use a very short time to calculation. Okay, here is the result I have get until now. So for bingo, we use this experiment parameters, and for the local shape, it can be constrained to the 161. And we also try to calculation for SKA band 1, band 2, and PUMA. And the result is shown here. And we are also calculating to see that if we improve the experiment parameters of bingo, and what will be the result. So now I get for the sky coverage, if we increase the sky coverage, the sigma will be smaller, but it seems to be converged. That means when we increase the sky coverage to a point, the FNL will no longer to be better. And also for the observation time, I have tried 1 year to 5 years, and it also can improve the result. Okay, here's the summary. And I have talked about the theory of the primordial Nagaussian entity, and I have introduced the 21 centimeter intensity mapping. And for the further step, I want to, in the calculation, to including the bias, because the bias can also have some Nagaussian entity effect. And I want to calculation the bingo abdas for this experiment configuration. What will be the constraint for the primordial Nagaussian entity? Okay, this is all my talk. Thank you.
Thank you. Questions? Any question? Okay, so thank you, Yusan, again. It was a pleasure to hear you. So now we can move to our next speaker, which is Dr. Champagne.
Can you see my slide?
Yeah, as you can see it, but it's not in the full mode.
Okay, great. All right, thank you everybody for the invitation. Should I get started?
Yes, sure, thank you.
All right, hello everyone. Thank you very much for the invitation. I'm Chen Feng from University of Science and Technology of China. So today, on behalf of Stage 4, I will show you some of the recent progress for the new physics study. So let me just turn off my screen. So this is an overview of what we have been investigating now. So we have a lot of ongoing projects looking for the new physics. Basically, these projects fall into 6 categories. So here I'm showing you those 6 different categories, like the early universe, dark matter, dark energy, and FRBs, modified gravity, as well as the component separation, etc. So this is a group focusing on the new models as well as the new approaches, like the component separation, etc. So today, I'm very happy to walk you through each individual project and highlight the recent progress a little bit. So first, the primordial Lagaussianity, some of you just talked about this project. And this has been a very interesting project for a broad community, like the CNB and intensity mapping. And here, I'm just showing you some of the recent results by Planck collaboration. And Planck has updated these results every 2 years. And from those 3 different papers, you see that they have already published the results for the constraints on the FNL. And the FNL is actually the amplitude of the curvature perturbation, as you can see from the first equation here. And from all those 3 different publications, it's very easy to notice that the sensitivity on the FNL parameter doesn't involve too much, indicating that it's really difficult to improve the sensitivity of this measurement. So this actually gives us a new idea to use the intensity mapping to constrain this parameter, because now we have 3-dimensional data cube to prove this parameter. And this is pretty optimistic, but in reality, we actually have other difficulties, such as the redshift space distortions the nonlinearities, etc. And these are the trade-offs we have to consider. But it's also checking, like Dr. Sang you just showed. We can get a very decent constraints on the FNL parameter. So as Dr. Sang just mentioned, now we are investigating 3 different shapes of the bispectra in the Fourier domain: the squeezed type, the equilateral, and orthogonal. And the most relevant one is the squeezed bispectra, which gives them dominant signal-to-noise ratios for this estimation. And Sang has already shown that this is by use of the bispectral formalism, and this is the generic formalism for the bispectra, and it's also the same for other probes like the CMB. So we can use this formalism to project the constraint on the FNL parameter. And to do this, you have to connect to the underlying physics, like the Bradley's temperature fluctuation encoded in this delta function. So eventually, we can just compare the measurements of the bispectra to this model to infer more information about the Bayesians, like the omega H1 and other parameters, etc. So this is the generic formalism to infer the physics from the bispectral formalism. And Dr. Sang, you just showed the recent progress for this calculation, and we can calculate all those functions for the bispectral. And hopefully we will get the results very soon. And Dr. Sang, you just showed the recent results using some specific tomographic redshift pairs to derive the limits. Of course, we have a lot of potential to improve the sensitivity. For example, we can use the full range of the redshift coverage, and we can also consider the Bingo-Abdas configuration to further improve the sensitivity for this investigation. So I think we are going to wrap up this work very soon, and the results will appear in the next year. So this is the study for the ERNIE universe, and we also paid much attention to the models of dark matter and dark energy. And for the dark matter models, we pay much attention to 2 species. One is the neutrino, another one is the axion. So for the neutrino, Dr. Xiaoling Feng now is investigating this problem. So the neutrino mass is really a mystery in particle physics, and is probably the last missing piece of the particle physics. And today, from the laboratory experiments, we can actually measure the difference mass square, but we cannot determine the 3 mass eigenstates because we still need another equation, which is the sum of the neutrino mass, which we want to infer from this intensity mapping experiment. So if we can get the sum of neutrino mass, then we can probably determine the 3 eigenvalues of the neutrino masses, and we can infer the correct mass hierarchy for the neutrinos, such as the normal hierarchy and inverted hierarchy, etc., which would be significant in science. So that's the big goal for our investigation, and apparently this is not unique for the intensity mapping, and the people in the CMB community has already studied this problem for decades. And here I'm just showing you some of the recent results, combining all of those different forecasts. And apparently we can get a really interesting limits for the sum of neutrino masses. So to determine the correct mass hierarchy, we need to reduce the sum of the neutrino masses down to 50 MeV. So apparently from all these combinations, we can achieve this goal very easily. And it's also very interesting to see how well we can infer to determine some of the neutrino masses from the intensity mapping alone. So Dr. Xiaoling Feng now is currently looking into this problem. So he first investigated effects of these neutrino masses on the matter power spectrum. So on the matter power spectrum on the left-hand side, this is the matter. So you see the effects due to the different masses of neutrinos. And if we just calculate the difference between the neutrino mass affected power spectra and the standard lambda CDM model, we get this the bottom left, the deficit. So this is basically showing you the suppression due to the non-zero neutrino mass. And from the level of the suppression, it's an indicator of the neutrino masses. So this is how we infer the neutrino mass from the matter power spectra. So in reality, we observe the matter power spectra with some frequencies. So we have to convert this matter power spectra to the angular power spectra at different frequency. So and it's very similar to the matter power spectra. We get a very similar suppression from this neutrino masses, and this and apparently from different neutrino masses we have different contribution to the suppression. And this is how we are going to infer the neutrino mass from the intensity mapping power spectrum. And this is the preliminary results using the Fisher matrix formalism. And Dr. Xiaolin Feng has already obtained these results. And the results look very promising, especially for the neutrino mass. We can get a very decent limits on the neutrino mass. But for the Fisher matrix prediction, the one concern is it could be very optimistic. So we have to incorporate more sophisticated simulations like the n-body simulations. And Dr. Ningfeng Xiao now is performing the n-body simulations to use the sophisticated models of this neutrino, this neutral hydrogen distribution to infer the neutrino properties. And this is the chart to show where we are now. We are investigating different problems. With the mark means we have already solved the problems. With the boxes means we are still looking into those issues. So we are at the end of this work. I think we are going to wrap up this work maybe early next year. So we are going to show the new results will come out. For this is the neutrino investigation. Another dark matter candidate, as I just mentioned, is the so-called axion. And axion has become a very interesting topic in recent studies. And people have been looking for new axion signatures from different probes like X-ray, gamma ray, etc. So intensity mapping, of course, is one of the interesting probes we have to look for its signature. And a student, Chen Suoniu at the USDC now is currently leading this project. So he took a two-step procedure. So the first step was to calculate this power spectra with the axion perturbations. So for this calculation here, I'm just showing you some schematic calculation. The first term is proportional to the density contrast. The second term is due to the resistivity distortion. And from the standard calculation, we can get the contribution due to those two perturbations. And if we include the axion perturbations, it will further modify those two contributions slightly. And Chen Suoniu has already done the calculation. And on the right-hand side, this is a plot showing you the effect due to the axion particles. And apparently, with different masses, the spectra show very distinct features. So this gives us a very big hope to isolate this property from the intensity mapping data. And we have already done some validation for this calculation and predicted the parameter limits using this technique. And it looks like it works very well. And then we moved on to investigate how well we can constrain the axion density contribution. And for example, the y-axis is the omega A is the energy density, the fraction of the energy density of the axion. And if this works, we can actually use the intensity mapping data to put constraints on the fraction of the axion density, energy density. So this would be really interesting to a broader community of the intensity mapping and other surveys like the CMB, etc. And for the study I just mentioned, we are just using, we just refine the power spectra in the linear regime. So if we have to go beyond the linear regime, for example, the nonlinear regime to very small angular scales, we have to take into account the corrections due to the nonlinearity. And in principle, this is very difficult. We have to use a model or we have to run very expensive n-body simulations. So there is another theoretical modeling for this nonlinearity is the so-called Halo model. So Bo Yuzhang, a student at USTC, so he is currently leading this project to extend the linear power spectra to nonlinear regime by using the halo model. So this is the halo model he's now incorporating. And from this halo model, he can calculate the two halo model terms. So one is the two halo term, which is the linear contribution, like I just mentioned from the axion study. Another one is missing from the previous study, which is the one halo term. And apparently at a small angular scales, we have to take into account the one halo term because it's not going to be negligible. And by using this halo model, we can get a full spectra of the neutral hydrogen power spectrum. And then we can get more information, especially at the small angular scales. And we also made a forecast for different projects to see how well we can use the small angular scale band powers to infer the physics from the small angular scales. And these are the results from different experiments. So our sensitivity is basically in the region between the linear and the nonlinear transition region. So probably we have to do a more quantitative estimation to determine the signal to noise ratio. And as we have done for the XM project, we also made some validation for this project. We first predicted the errors for the standard cosmological parameters, and this is the result. It looks like it works very well. And then we moved on to place constraints on the dark energy and the dark matter models. So here, dark energy, we code the W parameter, the equation of state, and we also place limits on the neutrino mass. And eventually, we can place the limits on those two different terms, like the one halo, two halo terms. And this is only possible when we have a halo model, when we have the two contributions. So this A2 refers to the so this A1 refers to the one halo term amplitude. So eventually we can determine the amplitude of one halo term from the future data, and this amplitude would tell us a lot of information about small scale physics like the baryonic feedback or other gaseous physics, etc. So it would be really interesting. So in addition to those fluctuation-based investigations, we also focus on the point source-like science, like the fast rate burst. And so far, we have been running simulations to understand the cosmology using the FRB. And Gabriel has been running the simulations to generate the FRB, assuming some relativity distribution and some experimental configuration, like the volume size and the signal to noise ratio. And eventually, we can simulate a catalog of FRB sources. And using this kind of simulated catalog, we can do cosmology using the FRB sources. And the idea is this. So we use the dispersion measure, and the dispersion measure consists of three different components. So one is coming from the host galaxy, which is poorly known. Another one is from our own Milky Way. Basically, we can measure it. And another one is the dispersion measure from the intergalactic media. And the dispersion due to the intergalactic media is actually an integral of the electron density along the line of sight. So from this FRB sources, we can determine the electron density at different directions. So this is how we can do the cosmology using the FRB catalog. And for this study, and Dr. Zhang Xue is leading this project. So she is considering three different assumptions for the dispersion measures of the host galaxy. And for example, the Gaussian case, which means we just assume the dispersion measure for the host galaxy is just a Gaussian distribution. And the other two variations, like one log normal and the two log normal cases. So Dr. Zhang Xue is currently making great progress for this project. Eventually, of course, we can compare the measured FRB sources with our existing technique, and we can get a lot of useful constraints for the underlying cosmology. And so far, Zhang Xue has already shown different results for different cases, assuming the dispersion measure of the host galaxy. For example, this is a Gaussian case and the one log normal case, and also she compared the constraints from the FRB unknown to the CMB constraints, and the CMB constraints are in red, and the blue curves are corresponding to the FRB constraints. Apparently, so far the FRB constraints cannot compete with the CMB constraints. But if we combine them, there might be a great chance that we can break the degeneracy between different parameters. So this would give us a good handle on the parameter degeneracy. And this is the beauty of this the extra data sets from the point sources. And in addition to the fluctuation-based science, the point source science, we also focus on new technologies. And so far, Alessandro Marin is a postdoc at USTC. So he is trying to incorporate a lot of features into the Mach domain, like the Lang-Gaussian beam and the polarization leakage, etc., and trying to recover the underlying neutral hydrogen signal from the raw data by taking account of those newly introduced features. And this might require us to come up with new ideas about the component separation, but we have to test that. And in this sense, we have a lot of new technique to develop for this aspect. And to summarize the current progress, this is just a short list of the active projects in this group now. And apparently we are having new members joining the group, and we are going to come up with new projects in the future, such as the modified gravity, which was missing from the previous chat. But now we have a student, Song Yanni from Yangzhou University. She's going to look into the issues regarding the modified gravity. And we are going to have a full spectrum of investigation for the new physics in the context of the bingo configuration. Thank you very much.
Thank you. So thank you so much, Xianfeng, for this nice presentation, the nice summary. Questions? Any no questions? Okay, so thank you again, Xianfeng. And now we can move to the next speaker, which is Alessandro Marins. Thank you so much, Alessandro, for being here with us. And we are sorry for this delay in the agenda. So feel free to start your presentation.
I'm in mute, sorry. No, my pleasure. Don't worry about that. Can you hear me clearly? It's okay?
Yes, you're
Nice.
listening very well.
So let me try here just a moment because I need to whoops, recover here. Okay. So thank you for this invitation. I'm Alessandro Marins from the University of Science and Technology of China in Hefei in China. So today I would like to talk a bit about how we can reconstruct 21 centimeter signals from the universe, mainly consider the bingo project frequency range and the cosmological time range, of course. So the schedule is described in this slide, for instance, giving a brief presentation about the 21 centimeter importance, some ideas to describe what we need to talk about in this presentation. For instance, the importance of the concentration of the 21 centimeters and neutral hydrogen and in some halos and so on, and we will see soon. So first of all, we are talking for these 2 days about 20 centimeters and the importance of this signal. So it's important only to concentrate and keep in mind that our goal here is to measure, but basically to measure this fluctuation here from the intensity, but described in brightness temperature units. So this unity is our goal, and we need to see and understand how our affects and what is concentrating information for us. So for instance, look in this plot here, we have some evolutions of our universe considering only 21 centimeters emissions, for instance, since the Dark Ages. By this time here, our redshift by 100, for instance, and this evolution for the average neutral hydrogen temperature or its fluctuation during the redshift and the cosmological epoch. So if you look at this point here, for Bingo, we are concentrating in this epoch post-reionization, where the most part of neutral hydrogen is concentrated in certain diamond Lyman alpha, dumped Lyman alpha, DL, and the signal is really, really weak. So the most part of hydrogen this epoch here after the reionization is completely ionized, but there are some portions of the emissions come from this DL, and this signal is really weak. For instance, we can see here in this description from this work, Villaes Navarro, here we can see, for instance, a simulation, a dynamic simulation for an halo in this with these masses. So if we can see within these masses halos here, we have a good concentration of the neutral hydrogen inside of the halos. For instance, here for redshift 0, but for redshift 0 and let me put here, okay, 0 and the smaller value of these masses is more concentrated inside of the halo. But when we assume, for instance, within this range here, we have almost all neutral hydrogen concentrated inside of the halos. As the paper published for Jajon mentioned, we have, for instance, this percentage of distribution of neutral hydrogen inside of halos for this period. For instance, considering only the Bingo region, is this one here is basically completely described from as a matter description, a matter tracer, the neutral hydrogen, of course. So as the neutral hydrogen is a tracer for the matter, total matter, it's important for us now understand what we want to do and what is our observation. Here we have the intensity mapping, of course, we are discussing about this for these 2 days. But here I would like to concentrate some information from the intensity mapping to have some ideas. For instance, of course, the intensity mapping, for the intensity map, it doesn't matter to identify individual sources. The most important is collect a global region here, concentrated inside of the beam on the sky, or the radio telescope resolution on the sky, like this one here, and collect all information within this region here. In this way, we can, for instance, collect information from even weak sources in distant places of the universe, and we can cover higher region on the sky. So just to give an overview of what we are assuming as a standard information here, of course, we are standard information is the Bingo region on the sky in the southern hemisphere, because we are plotting this design optical design for Bingo and the AGR, and assuming the AGR position and the optical design inclination, we can describe our region here. That is in this region -25 and -10 in declination, covering all right ascension. But here I will discuss more soon, but here for this goal here in this representation, I'm only assuming the same resolution for all beams, for all horns, for instance, to the bingo response. The other characteristics here, the frequency range, and so on. So just to give an idea, for instance, we have a lot of type of emissions beyond the 21 centimeter, of course. For instance, our galaxy is our most important contamination. So we have a lot of type of emissions from our galaxy, like synchrotron free, that is the emission come from interaction between chargers, particle charges, and heavy nucleus, and point sources where we can assume as we don't have resolution enough to identify what this type of emission outside of our galaxy, or even, for instance, nanograms dust spiraling in our galaxy interacting with our magnetic field, and of course the fluctuation of cosmic microwave background. So we can see, for instance, here all other astrophysical emissions in the bingo region, and comparing these emissions with our goal, 10 to 20 centimeters, we can see, for instance, that there are basically 4 level of magnitude difference between them. Of course, that is, to pound the bingo information, the 20 centimeter information is really, really hard for us. So we need to do a lot of type of pre-processing and post-processing of the data to actually recover this information. So, for instance, here we can see there are some regions we are covering, and the reason of this we can see, for instance, here, we are not masked this region, assuming all of a region that bingo will cover. We have this information here, this intensity, but the most part here comes from the galaxy, of course, for instance, here. And this can this can be a problem for us to recover 20 centimeters. So we can make a balance between which region we can cover, that we have so many influence from the other emissions, and the 20 centimeter that we can lose, of course. So, for instance, to mask our maps, we can assume some types of information. For instance, of course, first assume only the bingo sky region, but we can, for instance, cover certain regions of the galaxy emissions. Here, just to represent, cover 20% of the most strong pixels, or that is basically the most important emission from the foregrounds. And here, for instance, I'm blocking this emission from this region, assuming that, and combining this blocking with the bingo region, we have a new region to be assumed as signal important to collect information and reconstruct this signal. But of course, we can and we need to available with percentage. We need to use to collect this information. There, how I was saying, there's a balance between how much we are cutting from the galaxy emission and the podization on the boards, for instance. And here we can, of course, cut a lot of information from the galaxy, but otherwise we can also lose a lot of information from the 20 centimeters. So we have a balance. But on the other hand, for instance, certain type of blocking or cutting, or for instance, here, if you look here, we are cutting this region here, but this comes from certain strong point sources that can, for instance, result in a certain wiggles on our angular power spectrum, for instance. So just to represent the influence of this masking, for instance, we here are assuming 3 types of apodization or not apodization, using a cosine apodization on the boards. Here in green one, there is no apodization, 1 degree of apodization, and 5 degree of apodization. And the level panel here, we have 3 types of the constraints, cutting 10, 20, and 30% of foreground emissions. And we can see, for instance, the apodization influence basically, the more influence is basically on high L's, for instance, that it means lower angles. And for instance, we can see in the bottom panels here that we can remove such fluctuations, only constrain our regions, of course. But not only the mask is important, of course, we need to assume certain characteristics from our optical design. For instance, it's important to describe here again, to stretch out it, that the bingo optical design is really important for us, for instance, because this design provides us a really accuracy, a purity of our signal, but the most part come from the intensity, and the other polarization are much lower than the intensity. We have, for instance, describing our paper 3, a homogeneous description and coverage on sky, and we have the main lobe much better described, but by Gaussian 1, that is, we have lower side lobes. Here, only to describe these talks I was saying, for instance, we can see 2 types of the optical design description, assuming one, this here is double rectangular description with 20H feed horns, and here 33 feed horns. But we can assume this one here, each one of these feeds can move vertically up and down, up to 30 centimeters up and 30 centimeters down. So we can describe this in a homogeneous description on the sky. This plot here represents number of observation per pixel, identifier of pixel. In pink is represent double rectangular, and here this hexagonal is representing gray, for instance. So the optical design assumed by Bingo and the feed horn description has this good description of homogeneous that help us to recover very well our signals. And further that, for instance, I was saying the Bingo optical design is important, for instance, to achieve this information. The most part of signals are described by only intensity, but of course we have the other Stokes parameters, but here is in logarithm is the B, of course. So the masking, it's important to know about our instrumentation in our observation, and mainly which response our telescope has in certain position on the sky, for instance. As the Bingo has 20H feed horns and different places of our focal plane, each feed horn will have, for instance, a response on the sky, of course. For instance, if you get here a response of a feed horn on the sky near from the center of the focal plane, the response will be as Gaussian as possible. is good described in modeling by a Gaussian one. Of course, here is the main lobe and the side lobes around there, but it's basically symmetry bin. However, if you get far away feed horn response on the sky, we get now an asymmetric one, of course, and some aberration come from for us, and we can identify that it's not possible to get a good response and good modeling only using a Gaussian description. So for that, we need to use another modeling for assuming certain aberrations like Zarnik polynomials or other possibles to describe it in a good way. But for this work here, we are only assuming, for instance, that all information response for each feed horns on the sky will be similar like this one here, assuming only the main lobe, that is, will be the 30 arc minutes for all of them. We can, of course, for instance, like Professor Chanfan mentioned before, we are assuming some works currently analyze what is the effect when we include not only the main lobe, but the side lobes and our signals in our observation. We can model in this, but this is one is only for a symmetric beam response. So here we can, for instance, describe the sky signals observed and the response from our telescope convolved, and including the some instrumentation's information, and we can describe the response following certain types of models, for instance, Gaussian or Denk or cosine. Just to give, for instance, a visual idea, here we have two different type of observations. One for Bingo, that is, Bingo has the main reflector with 40 meters, and only one Mercat dish that has, for instance, 30.5 meters. So here in the top left, we have the simulated sky. And the following image here, we have this one here only convolved with the Gaussian beam. So here, only convolved with Gaussian beam come from Bingo, or only convolved with Gaussian beam from like the Mercat, only one dish from Mercat, of course. And when we constrain the Bingo region, we need to cut certain regions, and we can see, for instance, here, only these here emissions. And for instance, here only assuming Gaussian convolution or other types of convolution, where this type of convolution here, when we can see again here, there's some side lobes different from the Gaussian one. Gaussian one, there is no side lobes, but the cosine and Denk here describes certain lobes. For instance, this is for 1 Mercat, and here only for Bingo. So we can see side lobes around. The importance of this we can see, for instance, in this part here. For Gaussian, there are blur in certain point sources here, not point source emission, but point sources in this map. But here we have a better resolution when we assume certain side lobes. That is, the side lobe is important, but it can be a problem when we assume this effect in our map. For instance, if you have strong point sources, we need to understand well to remove this type of emissions. Otherwise, this will affect and to put worse our data. And of course, for instance, for one Mercat dish is impossible to describe in a good resolution. So of course, after that, the benefit of Bingo procedure of observation in a tomographic way is because we can have a tomograph analysis. That is, we can split in different channels and make spectrograph spectral analysis for each beam, for instance. And this help us, for instance, explore certain spectral information from the foreground. For instance, foreground is good described from some templates and has this smooth evaluation from the frequencies. Different from, for instance, 21 centimeter, that is basically Gaussian with some certain no Gaussian, as was mentioned in the previous presentation, and also the uncorrelated white noise here is completely no Gaussian. So we can explore this information, spectral information for each pixel on the sky to recover our signal, to discriminate what we want and what we don't want. So for that, for instance, we can use different types of algorithm. GENIUC is really important for us. For instance, it was the first one to recover 21 centimeters for bingo, but we are also including others to make cross-checking. For instance, GMCA is a good one, exploring different types of recovering, mainly describe this amplitude here. And just to give an idea, I won't concentrate in the model itself. We can discuss more if necessary later. But for instance, assume a certain type of model, the algorithm, we can see, for instance, here, these algorithms are blind component separation. That is, they are not assuming no information, prevalent information about the emissions. So for instance, they will be reconstruction the foreground and not 120 centimeters. Here we have our input, foreground input, that is the simulate foreground, and the foreground reconstruct from the GMCA, that is basically the same. And here we have, for instance, the difference between them, where here we have, for instance, the board effect, but it's not much important in this analysis here because there's only one, and just to give an idea, but it's really, really low. So it looks like the GMCA and other algorithm works well here, but we need to see not about the foreground, but about 20 centimeters. So if we can remove the foregrounds from our observation, for instance, here it's described for X, we are removing foregrounds for the X. We have, for instance, 81 centimeters, 81 signals, noise, here white noise, and possible some mismatching from the GMCA or about the other algorithm used. So here, for instance, we have this here that could be only H1 and noise, but we can identify our 21 centimeter or H1 signals, for instance. Here is our simulate H1 signals, and of course we can see here. But if we remove from this result here only white noise, we have this here. And even in this case, we can identify clearly our H1 centimeters, but we can see some patterns of our H1 centimeter, H1 signals. So we need to do a new procedure to remove this effect and mismodeling. This one is basically a statistic reconstruction. So we assume the two-point correlation in a harmonic space from that one here on R, that is this value H1 noise and the mismodeling from the algorithm, and correct this one by a suppression, where the suppression is assume that output divided by the prior here is on simulate 21 centimeters plus noise. That is, there is no influence from the modeling, the foreground modeling, and remove some influence from the noise here. And here we have our results, for instance, published last year and to be published again in the magazine soon. In green line, we have our white noise influence, which is important. In red one, we have the original 21 centimeters signal, and in blue dots, we have the reconstruction signals. Here we can see, for instance, we have a good accuracy in this reconstruction, and we can see, for instance, the residual difference here is basically really good. It's the same we can see, for instance, for the GNUC and FastSA, where as we are showing in our last paper. For instance, if you see some statistical comparisons between them, we can see in this moment, assuming only Gaussian beams for all feed horns and not introducing other no Gaussian or almost no Gaussian noise, GMCA, FastSA, and GNUC works really similar. There is no statistical difference between them. Here only to show, for instance, the other ones, the GNUC and FastSA, they are different, but statistically when we compare among 40 simulation, for instance, is basically the same. And the next step to include in our paper to be published again, we are providing some analysis from the HIDE. For instance, HIDE is a part of one of the pipelines of Bingo. And now, for instance, Felipe, Professor Fan, and Thiago Pena, we are producing some analysis about that to include the HIDE maps to reconstruct 20 centimeters. Here we can see, for instance, the heat maps from HIDE, that is the observation per pixel or from HIDE in this region, the radar reconstruction and the true, that is the simulated sky. We still have a different amplitude here, and we are working on that to identify which amplitude we need to change or fix to get the real results. But I believe soon we can describe correctly this amplitude here. After that, we can, for instance, apply again our algorithm to remove the foreground and identify our 21 centimeters. This is more realistic because are assuming the Bingo covered on the sky, of course. And finally, after the publishing of our paper again, we will be able to assume the more realistic reflectors. For instance, this is a work that we are doing with Professor Zichan Zhan from CSTC 54, for instance, constructing our dishes, and we can, for instance, put this design here into GRASP simulation and get our electric fields and then make our maps, of course. So it's important to include this and have the better reconstruction as possible to the realistic one. So in summary, of course, 81 centimeters is really weaker than the astrophysical contamination, mainly come from our galaxy. And we need to assume different types of information from our observation, from our instrumentation, and maybe constrain some regions to get more information on contaminated. And also, we are assuming some blending algorithms for the previous work, up to 3 algorithms used. Maybe include some new algorithms that developed from Professor Fan Chan and Professor Felipe Abdallah in this year. And for the next step, we are now include some other information, include side lobe effects on the data to bring reconstruction, and also include some secondary noise like porous leakage and 1/f by HIDE, and of course processing HIDE maps to obtain our pipeline working well, and include CTC CETEX 54 construction model and GRASP to get our results. Thank you so much.
Okay, thank you. Thank you. Do you have any questions, comments? So,
I believe I read in the time.
yes, you are quite in quite good on time. Thank you, Alessandro. Okay, so now we can have again a short 10 minutes break before the next talks. Okay, thank you, guys. Ah, Pablo e Eduardo, vocês estão me ouvindo?
Tá normal.
Vocês se importariam se a gente mudasse a palestra de vocês para o período da tarde, por causa desses atrasos que a gente teve aqui? Fica muito ruim para vocês?
Aí seria a partir de que horas, João?
Ah, a partir das 14 horas.
Não, tudo bem.
Mas se ficar ruim, vocês podem dizer, não tem problema.
Também tem que ver com o Gabriel e com o Pablo, porque eles estão em outro fuso, hein?
É,
Ah, o Pablo tá em outro fuso, né?
Os
Não,
dois, o
Gabriel pode
Gabriel e o
ser
Pablo.
agora.
eu posso ficar para depois, então, por causa do fuso dele, eu posso ficar para depois.
Porque o
Tudo
Gabriel
bem,
tá na
Eduardo?
Inglaterra e o Pablo tá na Holanda.
Ah, ok. Acho que a gente pode ter essas duas palestras então agora. E aí a gente pode deixar a tua então para o período da tarde, Gabriel? Eduardo,
Pode ser, João, pode ser.
pode?
Pode.
Ok. Desculpa, gente. A gente teve um imprevisto aqui com o som, com a chave do laboratório e acabou atrasando um pouco.
Não, tudo bem.
Oi? Pode fechar, Cleiton, por favor. Tudo hoje assim, acho que vamos chamar.
A corneta tem uma parte que é uma transição circular para um lado. E aí, nessa parte aqui, tem, se você for olhar lá fora, tem um lugar que vira em dois. O que acontece? Você pega toda a radiação que vem aqui, essa parte. Eu não sei porque isso aí você calcula exatamente. Mas quando a radiação passa, é separada. Então, mesmo a radiação fica uma celular esquerda. Aí quando chega aqui,
Okay. So let's going to start the next talk from Gabriel Horning. So thank you so much, Gabriel, for accepting our invitation, and please feel free to start your talk.
Okay, can you guys hear me?
Yes.
Okay, perfect. So about this talk, right? So it's the search for fast radial bursts, a forecast for the Bingo interferometer system. So I'll be talking about our job on simulating how good Bingo can detect and localize fast radial bursts on the sky. Oops. Okay, it's working properly. Okay, so a little bit about fast radial bursts, right? So they are radial transients on the sky, they are point sources, and we usually find them coming from outside our galaxy. Even there is some fast radial bursts that we could say that is coming from inside of our galaxies. The name is fast because they are bursts of with a duration from micro to milliseconds. They belong to the radio frequency from 300 megahertz to 80 gigahertz, and they are bursts because they are very energetic. So the energy is more or less about to 10 to the power of 32 joules, which is a power equivalent to 1 billion suns. The first radio burst found, its name is called the Lorimer burst, was identified in 2007, but this fast radio burst in particular was indeed detected in 2001. So it took more or less 6 years for Lorimer to identify this signal as strange and classifying as a fast radio burst. They are very special kind of signal as a radio transient on the sky, since they are very energetic and very fast. As you can see on this space phase right here of the radio transients, they occupy a very specific region, so they are very brief and very energetic. And because of their brightness temperature, we know that they must have some electromagnetic orange, so they can't be thermodynamic. Their origin can't be thermodynamic. But that's almost all we know about them because their origin is still unknown. They are likely to be magnetars because of some radio bursts fast radio bursts that we have detected on the past. But this is still unsure, and we already have detected hundreds of fast radio bursts. Well, and we have a lot of questions about them since they are so strange. So one of our first questions is, do all FRBs repeat? Because we know that some FRBs repeat with an interval of more or less like 16 days, and other fast radio bursts never repeat. But that doesn't mean that this fast radio burst doesn't repeat. It can just mean that the interval of the interval for this fast radio burst to repeat is longer. Like it could be years. And in this sense, do exist different classes of fast radio bursts that repeat? So some fast radio bursts repeat more briefly, others not. So this is kind of different physics that's happening there. We still don't know. Who are the progenitors? We also don't know this. As I said before, it could be magnetars, but some theories says that it could also be pulsars. Very unlikely though. And what's the emission mechanism? So let's say it's a magnetar, okay, but what's happening in that magnetar to emit this kind of signal? We have no idea about this. We have theories, okay, but there is no like I think that we know 100%. So these are this kind of questions that we want to know about the FRBs. Also, the FRBs can help us to understand all the kind of questions about the universe itself. I'm going to talk about this more later. And of course, Bingo can help to answer a lot of these questions. So how to search for these questions? We, of course, need to build telescopes. So I built this very simple chart to show some of the telescopes that are measuring fast radio bursts currently. So we can see that with the exception of Australia, which has 3 telescopes on the South Hemisphere, just Bingo is a telescope that is going to be built on the South Hemisphere. And this has a huge consequence on the sky map that we can do for the fast radio bursts, of course. So in this sky map, we can see that for the fast radio bursts that we already have detected, most of them are in the north sky, right? So this is a projection of the sky. This is a projection of the sky in galaxy coordinates. So the left-hand side of the sky of this chart is the northern sky, and the right-hand side is the southern. And we can see that the southern is poorly populated with a fast radio burst because we don't have that many telescopes looking for the southern sky. And it's very important to detect more FRBs on the southern sky, in particular because we have a huge part of the galaxy, the Milky Way, in the southern sky. And if we could detect an FRB coming from inside of our galaxy, this would be like a huge result, because this would help us a lot to understand from what is generating these FRBs. And since we have a lot of galaxies in the southern sky, this could help a lot. So I hope that with this, we could have justified the importance of Bingo detecting FRBs on the southern sky. Okay, so, but how to detect, how can we model the detection of the FRBs with Bingo, right? So we need some steps for this. Since there's a lot unknown about the FRBs, we need to do a lot of presumptions. So first we are going to, the most important of them is how to model the flux of the FRBs, right? So we have chosen one of the best model for the fluxes that we have available in literature, which is the model from Liu et al. Described it, where the flux for the FRBs is described by this function right here. Also, we have modeled the beams of our telescope as being Gaussian beams. So the interaction of our Gaussian beams and with the interaction with this flux peak is generating us this kind of results, as you can see here. So we did our simulation for 5 years of observations, and given that on this chart at the upper right-hand side here, we can see that as a function of this signal to noise ratio, we can detect FRBs coming from redshifts from 1.4 to 2. And yeah, we also created a mock catalog for the whole sky given this. And this other chart right here, we can see what fraction of the cosmological FRB is happening in our simulation we can detect with Bingo in 5 years. So these results are even competitive with CHIME, which is one of the telescopes that most can detect FRBs on the sky. So that previous sky map that I showed before that has a huge population of FRBs on the northern sky is mainly populated because of CHIME. CHIME can detect a lot of FRBs. I think that the last release of CHIME released something about 500 FRBs. There's a lot of signal. But Bingo is competitive with this telescope, which we can see on this chart right here, where you can see the beam angular size of Bingo with a detectable flux. As long as in this configuration right here, it's not as stronger as CHIME, but it's competitive with CHIME. And also there is the fraction of the detection flux, the fraction of the luminosity and the density flux of the FRBs that we can see on the cosmological mock. But there is a problem with this, because just to detect the FRBs is not enough for us, because a lot of the cosmological information that we can get from the FRBs, in particular the redshift, can just came by detecting the FRB on the sky with a very high precision. This is crucial. So we need to do something that we used to call the localization on the sky rather than detect it. So if we can detect the FRB on the sky, it's good. We know that the FRB happened, but we need to know very precisely in the sky where the FRB happened. This is what we are calling a localization. And localization is not possible with just the main telescope Bingo only. So to be able to localize the FRB in the sky, we need an interferometry system. So that's the orange of the name, the Bingo interferometry system. Because using small units of telescopes, which we are calling here outriggers on different positions on the ground, we can use interferometry between these telescopes, very similar to a Michelson-Morley interferometer. We can increase our sky resolution because we are looking to the sky as fringe patterns, very similar in this GIF that I'm showing here. By looking at it to the sky in fringe patterns, we can increase by a considerable factor our resolution. The outriggers, I believe you people in AGI are very close to one of these outriggers. They are basically one of the Bingo horns, separately isolated from the main telescope. This is from this figure right here is from the outrigger from Uirapuru in AGI. Yeah. So we'll be modeling the interaction of the Bingo main telescope with this kind of outriggers, but also we're going to couple some mirrors in these outriggers to increase the full width at half maximum. To increase the resolution of the beam, so we can see further, deeper in the sky. One example of coupling the mirrors on these outriggers would be like this. This is just an illustration. Coupling the mirror in the horn would not be exactly like this, but it's just to illustrate the example. To do this, we need to do cross correlations. That's how the signal to noise ratio is calculated for cross correlations. So what would happen here is like the Bingo main telescope would be in this red dot. And in this example, we have 3 units of outriggers. We would put like the outriggers separated from the Bingo main telescope. Well, in a baseline of more or less 6 kilometers, the distance of each one of these outriggers and the Bingo main telescope. We have built some focal plane proposals right here. So how this works, we have been working with the configuration for the focal plane of Bingo of 4 columns and seven beams per column, which are pointing to similar directions on the sky, right? And these red crosses, as you can see here, are the outriggers pointing similar directions on the sky, but they are in different places on the ground, similar to the previous picture that I showed you before. So we have to run simulations for 5, 7, 9, and 10 outriggers. Note that for the 10 outriggers configurations, there are 2 outriggers pointing exactly in the same direction as the Bingo horns. So this is an example. And in particular, for each one of these outriggers configurations, we also run different mirror sizes. So the mirror size that we have chosen is 4 meters in diameter, right? 4 meters, 5, and 6. And this is an example for the 9 outriggers configurations with different mirror sizes. And these dashed circles right here, as you can see, is the size of the full width at half maximum of the beam from that horn. Of course, when we increase the diameter of the mirror, we also decrease in the size of the full width at half maximum. But the beam can see deeper on the sky. This has a huge difference because one can think that, okay, the 4 size mirror is going to detect more FRBs because the full width at half maximum of that outriggers is bigger, but the 6 meters configurations, it's true that it's going to detect less FRBs, but the FRBs that the 6 meters configuration is going to detect are going to have bigger redshift because because this configuration is kissing deeper in the sky. Okay, I'm not going to enter into details about the whole configurations because this is just going to be very repetitive. I'm going to explain a little about the results of these 9 outriggers configurations for the 6 meters mirror size, right? So by doing this, in a 5 years lifetime of the phase 1 of the telescope, we have calculated that Bingo would detect almost 300, almost 400 candidates. Candidates is a kind of signal that in our simulation, it could be an FRB. It doesn't have a signal to noise ratio very, very high. So it's barely higher to 1, greater than 1. So we are just classifying as candidates. The detections, we could detect like almost more than 100 FRBs during these 5 years. Where here detection is 1 single horn or the single telescope detecting the FRB without localization on the sky. And of course, the localization zone 1 and 2 baselines are the interferometric localizations. We are very interested in the localizations by 2 baselines because it has the best resolution that we can achieve here. And in 5 years of Bingo, we could detect 50 FRBs in 2 baselines in this configuration. But okay, we also know that Bingo is going to have an upgrade by using the phased array antenna systems using by Vivaldi antennas. And the advantage of these antennas is because opposite to the outriggers, which can only point to 1 direction of the sky, the Vivaldi antennas can build a large phased array station. And these phased array stations can look to many directions at the same time. And this is very good because we can cover a greater sky area, right? So in the upper chart, you can see here is the simulation for the phased array station of 6 meters, also for 5 years. And this increases a lot the numbers that we have. Now, instead of like 400 candidates, we have more than 800, so it doubles the number of candidates. But okay, we can't do much science with the candidates. We can still do something, but not a lot. But what we are interested here is with the detection, which more than multiplied by 7 times the detections. This is very good. And what we are interested in is the localizations, right? So you could see on the previous chart that the localizations in 2 baselines were 50. Now with this configuration here, we can detect more or less like 500 FRBs, which is very good. We can do a lot of science and cosmological constraints with these FRBs. We also have simulated a station of 40 meters, which is way bigger. And of course, the results also increases. The localization for 2 baselines in this configuration is like 700. So it increases by a huge factor the number of FRBs. Also, the detection is also increased, more than doubles compared to the phased array 6-meter station. Well, this is very important. We need to know the redshift of these forecasts, right? So for the first result, just using 9 outriggers with 6-meter diameter mirrors is going to be this blue histogram right here. We can see that the vast majority of the FRBs localized in 2 baselines have a redshift between 0 and 0.5, which is nice. But our best result has a lot of FRBs localized between 0 and 1 or even 1.5, having some fast radial bursts even with a redshift of 3.5, which is very good and very important. So what's the importance of knowing the redshift of these FRBs, right? So this is very useful because when an FRB leaves its galaxy and it comes to us, it carries a lot of information about the way that it's traveling, right? So it carries the information about the galaxy host, about the environment, because the fast radial burst travels to some dust, and this does affect the dispersion measure of the signal. Also carries information about the universe itself, because when it leaves the galaxy, it starts to travel between the intergalactic medium, so it carries this information. And also gives us information about our own galaxy. When it comes to inside the Milky Way, the dispersion measure caused by the Milky Way and the Milky Way halo also appears in the observations. And in particular, for the cosmology point of view, this is very important because the dispersion measure of the intergalactic medium can provide us a very important information about the acceleration of the universe, about the quantity, about the amount of baryonic matter inside the universe, and the amount of dark matter as well. And this is a work in preparation also by Bingo team, where we are using this simulations catalog that we have produced in this paper right here to build some forecasts for what cosmology can Bingo constrain with these FRB results together with the other FRBs available in literature. Okay, that's for the talk, our finances, our funding, and our universities. And that's it. Thank you very much, everyone.
Thank you, Gabriel. Thank you so much for such a nice presentation. Questions, comments? No?
Hello, Gabriel.
Hello.
When you say about the 6 meter of the after trigger, the mirror, what do you mean exactly? So it's like the main bingo use a major 6 meter mirror to like in the main bingo that has the mirror. So for the after trigger, also can have a mirror.
Yes. Yeah. So an outrigger can have a mirror just like this. So an outrigger is just in a bingo horn, right? So just like this, like bingo rapuru. We can couple a mirror in this horn. So that's an example of how it could be. I'm not 100% sure if this is the final result. I'm most certain than not, because this is a circular mirror. I don't know if the mirror in the real life would be circular like this. I am most sure that no. But if you couple a mirror in the horn, would be mostly like this. So there would be this dish, extra dish in the horn. And the diameter of this dish would be 6 meters. The same for 5 and 4 meters. Yeah, would be like this.
What will be the phased array? Phased array means use several horns together.
No, so the phased array is kind of different. Because well, I don't have any picture for phased arrays right here. But phased arrays are a schematic of smaller antennas that are positioned on the ground. Yeah, I don't have any picture right here. But these antennas are spaced by each other. So because of the space of each other, we can control the phase of each antenna. So we can create beams in each antenna because of the phase difference of each antenna. That's how the antenna is going. That's how one phased array station can point to many directions. So it's not like many bingo horns. It's a different case, and the fact of being 6 meters and 4 meters has not anything related to a mirror size for the phased array station. It's literally the size of the station of the phased arrays. I'm not sure how to position this phased arrays on the ground and how the 6 meters configuration is going to appear on the ground, but it's characteristic length for the phased array station, and it's comparable with the size of the mirror, because on this, for example, on the 6 meters phased array configurations right here, effectively on the simulation, it's like we are having a lot of bingo horns with 6 meters dishes. Effectively, it's like this in the simulations, just mathematical stuff. It's the same, but on the ground, it's different. That just because with the outrigger we can just create one beam, but with the phased arrays we can create a lot of the beams very similar to the beams of the outriggers.
Okay. So you mean the 40 meters is actually the diameter of the array, right?
Yeah, for the 40 meters station would be like a lot of bingo horns with a dish or mirror, if you prefer, with a dish of 40 meters, which of course we can do, right? But because we can't couple a mirror of a diameter of 40 meters on a single horn, but we can do this with phased arrays. Not coupling a mirror, but we can build a phased array station of 40 meters, and it's equivalent. Sorry, it's not equivalent. It's better because with the phased array stations we can have a lot of beams coming from there.
And how many is phased array? Only one, or a lot in your calculation in your paper?
Yeah. So on the paper that we have released, on the paper that we have released already, we don't have phased array analysis for that paper. This phased array analysis is in a preparation paper yet. So on the paper that we have released with Marcelo, Ricardo, and I, we have just put the analysis using outriggers. This phased array analysis is in preparation paper. But yeah, let me see here.
Important to highlight. Pablo will comment more about the phased arrays in the next the presentation.
Yeah. Pablo knows better about the instrumentation of phased arrays than me. But for example, on this chart right here, for the 40 meters, we can, from just one phased array stations, we can have almost 200 beams coming from there, or just one phased array station. So it's very powerful.
Okay.
Thank you very much. Nice discussion. Maybe you can discuss a little bit more.
Yeah, for sure.
Later or offline. Thank you, Gabriel, again. Thank you so much. So now we are going to have the last talk of this morning, presented by Pablo Mota. So Pablo, please feel free to start your talk.
Hello, everyone.
Hello.
Can you hear me?
Yes, we are listening very well.
Yeah, thank you for the invitation. I will share my screen with you. Yeah, this problem is happening again. All right. Yeah, you're seeing everything black, right?
Yes, everything is black here.
Yeah, I thought I fixed this, but it's still happening. Well, can someone share the slides for me?
Yeah, I can. You only need to send to me.
Mm,
Please send by Skype.
okay.
Did you send?
Mm.
Because I didn't got
Wait,
anything.
I can send you by email. Okay.
Oh, come on. Maybe it's hard for me. Let me see. Okay, just to download here. Mm. Did you send it?
Yeah.
Which
Did you find
mail?
it?
Gmail or
Gmail.
USDC?
Oh, sorry, I sent the USB.
No, maybe USDC. I need to get here. It's because I need to turn on my VPN to access my email here. I don't have it with USDC. Okay, if you okay, I got it. Just a second. just finish.
Sorry for this. This happened before, but I thought it was fixed already.
To the moment, because to access my Gmail is a bit
Would you like
hard
to
here.
send me?
No, it's almost here.
Você pode fazer, Pablo, a apresentação daqui a 2 horas.
Não, eu tenho agora aqui. Já tenho aqui.
Achou?
Eu vou. Baixou. We'll turn off here my VPN just a moment. All right. Can see?
Yeah.
Okay, wait, turn off my mic.
Also, the idea of this presentation is to talk about the constraints from the H1 things to mapping. So this is a paper that it's finished and hopefully will be circulated and submitted very soon. So I'm happy to share with everyone the results that we got. First of all, let's recall that the main science goal of Bingo is cosmology. And the way that Bingo do cosmology is because Bingo is an intensity mapping experiment. And with intensity mapping, Bingo can measure sky maps of the H1 brightness temperature. And the H1 brightness temperature, we can assume that is a tracer of the underlying matter. Okay, so if we take together Bingo with other experiments such as CMB experiments, we can get very good constraints in the cosmological parameter. Right, so the framework of this statistical analysis, it's the Bayesian inference. So the Bayesian inference is based on the Bayes theorem that relates conditional probabilities. So for parameter inference, we relate the probability of theta, where theta is an array of parameter given our data set, with the probability that we call likelihood, that would be the probability of D given theta. And for this, we also need the prior distribution and the evidence. The prior distribution is our initial beliefs of what these parameters are, and the evidence is just the integral of the likelihood. So if you have a sample of different thetas, and then we compute the likelihood for all this sample, we can get what is our posterior probability. So those are our priors assumptions. So we assume a flat prior for all the cosmological parameters with a fair range of interval. And apart from our 6 key cosmological parameters, we also have nuisance parameters. So we have 30 redshift beams for Bingo, and for each redshift beam, we sample 2 nuisance parameters, the bias, and also the omega H1 times bias. And next we have the likelihood. So assuming flat priors, we can just get the posterior from our likelihood function. So we use a Monte Carlo method to sample the parameter space in a way that converts towards a region of towards a volume of high likelihood. And the likelihood is computed with the given formula, where it's given by the theoretical angular power spectrum and also with the measurements. And we also need the covariance as a way of as an estimate of our uncertainties. Next, so I'm going to explain here how we did the bingo simulations. So we took our we first need a simulation of the 21 centimeters, and we did this using a fitting from brightest temperature histogram from the mock maps from Zhang et al. So in this paper they did some mock maps based on in-body simulations and distribution and H1 over these in-body simulations. So fitting this distribution of brightness temperature, we can have what is this log normal distribution that the 21 centimeter should have. And given this, we created a full set of 500 log normal simulations of the cosmological 21 centimeter signal. And also the bingo simulation encompasses 3 different ingredients, because apart from the 21 centimeter signal, we also need to assume what is our white noise map. So assuming the bingo phase 1 operation and this optical arrangement of 28 horns that is described in your collaboration paper, we generated random noise maps. And also we are taking account we are also taking account the residual of foreground removal. And this was done, and Alessandro have explained it to you about some of the foreground removal techniques, and this foreground removal produces a residual, right? So instead of applying this method over and over to all our maps, we are taking this previous computed residual and applying to our map. So our final bingo simulation is a summation of the 21 centimeters, the white noise, and these residuals. So this gives a full simulation of bingo that taking account all these source of errors. Next. And the way we do the measurements is you can see there on the left plot the CLs of the 21 centimeters, and in the right plot you have in the yellow curve you have the white noise, and for the large L's this white noise dominates over the 21 centimeter signal. So we need a way to remove this information of the white noise, and we do a debiasing procedure where we remove what is the expected value of this white noise by taking an average of 100 white noise simulations, and we take this average and we remove from the total signal. And you can see go back, please. and the red curve of this plot is the residual. You can see that it's overall it's very small. So it's just a little high for the lower multiple. So even when we do this debiasing procedure, we still can have some high power in low multiples due to this residual, but we are cutting off the small L, so these high multiples in low L's is not a problem. Next, we computed a covariance matrix from these 500 simulations that taking account all these error sources. So you have the 30 redshift beams and some plots of the covariance matrix for all the redshift beams. Next, you can see the next slide, please. This is an interesting way of seeing the covariance matrix that is a normalization that is the Pearson correlation, right? So we are normalizing by the diagonal values. So it's interesting to see that for the pure 21 centimeters, the log normal field here have a high Pearson correlation for the highest multiples, but when we have the white noise and the residual Faguera removal all included, we are not seeing this high Pearson correlation here for the high multiples, since we have the Gaussian white noise added on top of the 21 centimeter signal, and this large L is where the white noise dominates. So next, I will show here the results that we got from the parameter constraint using from the simulations, and you can see there what is the best curve fit compared to our data points of our simulation, and also the blue shadow area there is the interval of multiples that we are using for our analysis. And you can see that we get there a reduced chi-square of 1.07 that shows out that this is a good fit for our data. So now let's see some of the contour plots for these simulations. Next, yeah. So in this plot here, I am showing what are the contour plots, taking account just the bingo data, and there I'm comparing 3 different realizations of bingo. So it's interesting to see how much we can trust these contours, or how much they can be biased by the individual realizations. So in the next contour plot, in there you can see here a comparison of the contour plots for the pure 21 centimeters, and also when we include the error sources of the white noise and of the residual, and you can see that we can get very consistent contour plots there. So these contour plots are even more overlapped than compared to the other one. You can see that here that we are taking the same log normal realization, but just included the error sources there. We can get very consistent results. And here we can see the contours of the Planck 2018 compared to the Planck 2018 plus Bingo. So you can see that we can get really good constraints when the Planck and Bingo are together, and also you can see that when we included all the error sources on the simulation, we can get very consistent results. And then the next one is the same plot, but comparing for different realizations of the simulation. So you can see there how good the constraints are and the consistency between all the different realizations. And since we are also sampling the nuisance parameters, not just the cosmological one, I can show there that we can get when we have Bingo plus Planck, we can have a good constraint of the nuisance parameters for all the redshift beams, as you can see there in this plot. And next, please. I show you some of the chi-square values of all these simulations that we ran. So the next steps are there are some extended analyses that are on the way with other people of the collaboration. For instance, we have some work on progress from Luisa of dynamical dark energy and dark matter interaction, and also neutrino physics with Li Fan, and there's also someone working with modified gravity. So I'm happy that people can take the same data products and the same tools to explore new physics with Bingo. Thank you. I would like to thank the Bingo telescope for this opportunity, and also FAPES for the financial support. Sorry for the time. I know you have lunch now, but if you have any question or comment, I'm glad to answer.
Okay, thank you. Thank you so much, Pablo. So if you have any questions or comments.
Sorry, I was thinking you will comment about the phase arrays.
Yeah. Yes. Sorry, I didn't comment anything about the phase array. So
would you like to ask something? Maybe later he can ask you directly for.
Okay, no problem. Actually, I have a question about your talk. So for different realization, why the control deviate a lot?
It's interesting to compare different realization, and here we are assuming a log normal distribution, and for those log normal distribution, and the random errors, they are really correlated, and they can this correlation is so high that they can give an effect of some shifts in the power spectrum. So this is why there is some shift when we compare different realizations, but you can see they are still consistent within the 1 sigma level.
Okay.
Okay, so thank you very much, everybody, and thank you for your attention. And I'm so sorry again for the delays that we had today. So we're going to stop here the morning section of today, and we come back at 2:30, sorry, p.m. here in Brazil after lunch. So thank you very much.
Obrigado, João. Obrigado a todo
Obrigado,
mundo.
pessoal. Obrigado mais uma vez. Obrigado pela compreensão aí. Thank you,
Thank you.
Sam, for being here up to now.
Thank you.
Thank you, thank you.
Thank you.
Então, às 2h30 a gente retoma, tá certo, pessoal? Obrigado.